2, 1, 2, 1, 2. Hair looks wild right now. Whatever. So, all right. Is this working? Looks like it's working. Okay, cool. So, picking back up with picking back up in this built machine learning model skill path. So, did carry nearest neighbors. Now I'm on to logistic regression. This is within the larger umbrella of supervised learning introduction to classification. So, logistic regression. Introduction. When an email lands in your inbox, how does your email service know whether it's real or spam? This evaluation is made billions of times per day. And one possible method is logistic regression. Logistic regression is a supervised machine learning algorithm that predicts the probability ranging from 0 to 1 of a data point belonging to a specific category or class. These probabilities can then be used to assign or classify observations to the more probable group. For example, we could use a logistic regression model to predict the probability that an incoming email is spam. If that probability is greater than 0.5, we could automatically send it to a spam folder. This is called binary classification because there are only two groups, e.g. spam or not spam. Some other examples of problems that we could solve using logistic regression: disease identification. Is a tumor malignant? Customer conversion. Will a customer arriving on a sign-up page enroll in a service? In this lesson, you will learn how to perform logistic regression and use it to make predictions. If you're unfamiliar with logistic regression, we recommend you review it before proceeding. Otherwise, let's dive in. Sorry if you're unfamiliar with linear regression, but we're familiar, so let's dive in. Code Academy University's data science department is interested in creating a model to predict whether or not a student will pass the final exam of its introductory machine learning course. They plan to accomplish this by building a logistic regression model that predicts the probability of passing based on the number of hours a student reports studying. Run the code in script.py to plot the data. 0 indicates that a student failed the exam, and 1 indicates that a student passed the exam. So looks like if you want to be confident that you're going to pass, you need about 13 hours or more of study. How many hours does a student need to study to pass the exam? Linear regression approach. With the data from Code Academy University, we want to predict whether each student will pass their final exam. Recall that in linear regression, we fit a line of the following form to the data: y equals b0 plus b1 x1 plus b2 x2, and so on to bn xn, where y is the value we are trying to predict, b0 is the intercept of the regression line, b1, b2 to bn are the coefficients, x1, x2 to xn are the predictors, also sometimes called features. For our data, y is a binary variable equal to either 1 passing or 0 failing. We have only one predictor, x1, num hours studied. Below, we've fitted a linear regression model to our data and plotted the results. The best fit line is in red. We see that the linear model does not fit the data well. Our goal is to predict whether a student passes or fails. However, a best fit line allows predictions between negative and positive infinity. We've provided you with the code to train a linear regression model on the Code Academy University data and plot the regression line. Run the code and observe the plot. Expand the plot to full screen for a larger view. Using the regression line, estimate the predicted outcomes given by the line for students who study 0 hours, that's a 0, 10 hours, that's a 0.5, and 30 hours, let's say 1.75 or something higher. Save the results to Slacker, average, and studies. Value for Slacker is incorrect. student who studies 0 hours. Oh, sorry, that's actually negative. We'll call that negative 0.2. Logistic regression. We saw that predicted outcomes from a linear regression model range from negative to positive infinity. These predictions don't really make sense for a classification problem. Step in logistic regression. To build a logistic regression model, we apply a logit link function to the left-hand side of our linear regression function. Remember, the equation for a linear model looks like this, right there. When we apply the logit function, we get the following. The natural logarithm of y over 1 minus y equals b naught plus b1 x1 plus b2 x2 all the way to bn xn. For the Codecademy University example, this means that we are fitting the curve shown below to our data instead of a line like in linear regression, which makes a lot more sense. Notice that the red line stays between 0 and 1 on the y-axis. It now makes sense to interpret this value as a probability of group membership, whereas that would have been nonsensical for regular linear regression. Note that this is a pretty nifty trick for adapting a linear regression model to solve classification problems. There are actually many other kinds of link functions that we can use for different adaptations. We've provided the code to build a logistic regression model on the Codecademy University data and plot the fitted curve. Take a look at the plot, expand the plot to full screen for a larger view. Using this curve, estimate the probability that a student who studied for 5 hours will pass the exam. Save the result to 5-hour studier. So I'll call that 0.05. Log odds. So far, we've learned that the equation for a logistic regression model looks like this. Note that we've replaced y with the letter p because we are going to interpret it as a probability, e.g. the probability of a student passing the exam. The whole left-hand side of this equation is called log odds because it is the natural logarithm, ln, of odds, p over 1 minus p. The right-hand side of this equation looks exactly like linear regression. In order to understand how this link function works, let's dig into the interpretation of log odds a little more. The odds of an event occurring is odds equals p over 1 minus p equals p event occurring over p event not occurring. For example, suppose that the probability a student passes an exam is 0.7. That means the probability of failing is 1 minus 0.7 equals 0.3. Thus the odds of passing equals 0.7 over 0.3 equals 2.33 recurring. This means that students are 2.33 times more likely to pass than to fail. Odds can only be a positive number. When we take the natural log of odds, the log odds, we transform the odds from a positive value to a number between negative and positive infinity, which is exactly what we need. The logit function, log odds, transforms a probability, which is a number between 0 and 1, into a continuous value that can be positive or negative. Suppose that there is a 40% probability of rain today, p equals 0.4. Calculate the odds of rain and save it as odds of rain. So note that the odds are less than 1 because the probability of rain is less than 0.5. Feel free to print odds of rain to see the results. Use the odds that you calculated above to calculate the log odds of rain and save it as log odds of rain. I actually don't know how to do a natural logarithm in Python. I'm gonna guess np.ln. Suppose that there is a 90% probability that my train to work arrives on time. Calculate the odds of my train being on time and save it as odds on time. Note that the odds are greater than 1 because the probability is greater than 0.5. Use the odds that you calculated to calculate log odds. Sigmoid function. Let's return to the logistic regression equation and demonstrate how this works by fitting a model in SciKit-Learn. The equation is that natural log of p over 1 minus p equals b0 plus b1 x1 plus b2 x2 all the way to bn xn. Suppose that we want to fit a model that predicts whether a visitor to a website will make a purchase. We'll use the number of minutes they spend on the site as a predictor. The following code fits the model. From SciKit-Learn.linear model, import logistic regression, model equals logistic regression, model.fit, min on site, purchase. Next, just like linear regression, we can use the right-hand side of our regression equation to make predictions for each of our original data points as follows. Log odds equals model.intercept plus model.coef times minutes on site, print log odds. Output is this array. Notice that these predictions range from negative to positive infinity. These are log odds. In other words, for the first data point, we have ln of p over 1 minus p equals negative 3.28 and so on. We can turn log odds into a probability as follows. So we take this, then we take e, so we can separate this by getting, what is e again? E is the, what is e? I mean, come on, I know e, but what is it? What is e again? Euler's number, or Euler's number, I think that's how that's pronounced, or the natural logarithm's base. E is an infinite decimal that is approximately that and is used to model exponential growth or decay. Got you. So back here. So since e is the base of the logarithm, we can free the p over 1 minus p by taking the e to the negative 3.28 power, and then p equals e to the negative 3.28 times 1 minus p. So essentially we're just solving for p. In Python, we can do this simultaneously for all of the data points using numpy loaded as np. np.exponent log odds divided by 1 plus np.exponent log odds. Output array. Now all those numbers are turned into a probability between 0 and 1. The calculation that we just did required us to use something called the sigmoid function, which is the inverse of the logic function. The sigmoid function produces the S-shaped curve we saw previously. In the workspace, we've fit a logistic regression on the Codecademy University data and saved the intercept and coefficient on hour studied as intercept and coef, respectively. For each student in the dataset, use the intercept and coefficient to calculate the log odds of passing the exam. Save the result as log odds. And save the intercept and coefficient on hours studied as intercept and coefficient, respectively, for each student in the data set. So, okay, let's think about what we're doing, right? We import pandas, import numpy, codecademy equals pd.readcsv, codecademy.csv, fit the logistic regression model, hours studied equals codecademy hours studied, so that whole column, past exam equals Codecademy U, past exam, that whole column, from SciKit-Learn.linear model, import logistic regression, model equals logistic regression, model.fit, hours studied to past exam, save the intercept and coefficient, intercept equals model intercept, coefficient equals model.coef, calculate the log odds here, log odds equals none, print log odds, and each student in the data set use the intercept and coefficient to calculate the log odds of passing the exam, say the result is log odds. So what would it be for this is an array, so it has to be for I in range length of hours studied. Log odds. Does it want us to make an array? So wouldn't it be I feel like this isn't right, but whatever. Intercept plus model.coef times min on site, but I want hours studied. I feel like I'm doing this very wrong. Oh, okay, pay attention. We can do this simultaneously for all of the data points using NumPy loaded as NP. But first we have to save this to log odds. Okay, so I don't need to do this though. So it's just model.intercept plus model.coef times hours studied. Now convert the predicted log odds for each student into a predicted probability of passing the exam. Save the predicted probabilities as pred probability passing. So that'd be np.exp log odds divided by 1 plus np.exp log odds nice. Fitting a model in SciKit-Learn. Now that we've learned a little bit about how logistic regression works, let's fit a model using SciKit-Learn. To do this, we'll begin by importing the logistic regression module and creating a logistic regression object. From SciKit-Learn.linear model, import logistic regression, model equals logistic regression. After creating the object, we need to fit our model on the data. We can accomplish this using the .fit method, which takes two parameters, a matrix of features and a matrix of class objects, the outcome we are trying to predict. Model.fit features labels. Now that the model is trained, we can access a few useful attributes. Model.coef is a vector of the coefficients of each feature. Model.intercept is the intercept. The coefficients can be interpreted as follows. Large positive coefficient, a 1 unit increase in that feature, is associated with a large increase in the log odds. and therefore probability of a data point belonging to the positive class, the outcome group labeled as 1. Large negative coefficient, a 1 unit increase in that feature is associated with a large decrease in the log odds probability of belonging to the positive class. Coefficient of 0, the feature is not associated with the outcome. One important note is that SciKit-Learn's logistic regression implementation requires the features to be standardized because regularization is implemented by default. I'm going to read that again. So let's fit a model using SciKit-Learn. To do this, we'll begin by importing the logistic regression module and creating a logistic regression object. So from SciKit-Learn.linearModel, import logistic regression, model equals logistic regression. After creating the object, we need to fit our model on the data. We can accomplish this using the .fit method, which takes two parameters, a matrix of features and a matrix of class labels, the outcome we are trying to predict. Now that the model is trained, we can access a few useful attributes. Model.coef is a vector of coefficients of each feature. Model.intercept is the intercept. The coefficients can be interpreted as follows. Large positive coefficient, a 1 unit increase in that feature, is associated with a large increase in the log odds, and therefore probability of a data point belonging to the positive class, the outcome group labeled as 1. Large negative coefficient, a 1 unit increase in that feature, is associated with a large decrease in the log odds / probability of belonging to the positive class. Coefficient of 0, the feature is not associated with the outcome. One important note is that SciKit-Learn's logistic regression implementation requires the features to be standardized because regularization is implemented by default. We've pre-processed this data and split it into training and test sets as follows. Xtrain is the feature matrix containing standardized training data for our studied and practice test score. Ytrain contains the outcome variable for the training data, whether or not each student passed the final exam. 1 indicates passing, 0 indicates failing. Create a logistic regression object named CCLR and fit it to the provided training data. Print out the coefficients and intercept for the model. Are the coefficients positive or negative, and does this match your expectation? Which feature, our studied or practice test score, is more strongly associated with students' probability of passing the final exam? Intercept. The coefficients are positive. Does this match my expectation? I don't even know if it should. Using a trained model, we can predict whether new data points belong to the positive class, the group labeled as 1, using the .predict method. Using a trained model, we can predict whether new data points belong to the positive class, the group labeled as 1, using the predict method. The input is a matrix of features, and the output is a vector of predicted labels, 1 or 0. So print model.predict features, sample output would be 0, 1, 1, 0, 0. If we are more interested in the predicted probability of group membership, we can use the .predict proba method. The input to predict proba is also a matrix of features, and the output is an array of probabilities ranging from 0 to 1. So print model.predict proba features, colon, comma, 1, sample output 0.32, 0.75, 0.55, 0.20, 0.44. By default, predict proba returns the probability of class membership for both possible groups. In the example code above, we've only printed out the probability belonging to the positive class. Notice that the data points with predicted probability is greater than 0.5. The second and third data points in this example were classified as ones by the .predict method. This is a process known as thresholding. As we can see here, SciKit-Learn sets the default classification threshold probability as 0.5. In the workspace, we fit the same logistic regression model on the Codecademy training data. We've also created X-test and Y-test, which contain the testing data. Use the predict method to predict whether the students in the test dataset will pass the final exam, then print out the resulting vector of predictions. Zero, 1, 0, 1, 1. Now use the .predict proba method to calculate the predicted probability that each student in the test dataset will pass the exam. Print out Y-test. Oh, I think it wanted us to just do that it would pass. And what this is doing is up to, I don't know, up to a space. Is that what it's doing? Print out X-test to see whether the students in the test dataset actually passed the exam. Did the model make accurate predictions looking at the probabilities? Oh, print out Y-test. Did it make accurate probabilities? Not exactly. In this case, it seems that although 11 is above 10, which seems to be the cutoff point, or no, although 11 is above 10, which seems to be what it's treating as. No, actually, I'm confused what it's treating. Oh yeah, 0.5 is what it's treating as the cutoff point, but even though 11 is over halfway, it still counts as a fail. As we've seen, the logistic regression is used to predict the probability of group membership. Once we have this probability, we need to make a decision about what class a data point belongs to. This is where the classification threshold comes in. The default threshold for SciKit-Learn is 0.5. If the predicted probability of an observation belonging to the positive class is greater than or equal to the threshold, 0.5, the data point is assigned to the positive class. So here we see the threshold is 0.5, predicted probability of cancer, number of individuals below the threshold are predicted as not having cancer, individuals above the threshold are predicted as having cancer. Striped areas are incorrect predictions. We can choose to change the threshold of classification based on the use case of our model. For example, if we are creating a logistic regression model that classifies whether or not an individual has cancer, we may want to be more sensitive to the positive cases. We wouldn't want to tell someone they don't have cancer when they actually do. In order to ensure that most patients with cancer are identified, we can move the classification threshold down to 0.3 or 0.4, increasing the sensitivity of our model to predicting a positive cancer classification. While this might result in more overall misclassifications, we are now missing fewer of the cases we are trying to detect actual cancer patients. In the workspace, we fit the same logistic regression model on the Codecademy U training data. We've also printed the predicted classes and true classes for the test data. Take a look at the predicted probability of passing the exam for the misclassified data point. The predict method uses a default threshold 0.5 for predicting group membership. For this example, we would correctly classify all 5 data points in the test data set using a different threshold, set the value of alternative threshold to any value that would accomplish this. Where's alternative threshold? Confusion matrix. When we fit a machine learning model, we need some way to evaluate it. Often we do this by splitting our data into training and test data sets. We use the training data to fit the model, then we use the test set to see how well the model performs with new data. As a first step, data scientists often look at a confusion matrix, which shows the number of true positives, true negatives, and false negatives. For example, suppose that the true predicted classes for a logistic regression model are y true equals 00111, 00101, y pred 011, and so on. We can create a confusion matrix as follows. From SciKit-Learn.metrics, import confusion matrix, print confusion matrix, y true, y pred, array 3214. This output tells us that there are 3 true negatives, that there are 3 true negatives, 1 false negative, 4 true positives, and 4 false positives. Ideally, we want the numbers on the main diagonal, in this case 3 and 4, which are the true negatives and true positives respectively, to be as large as possible. In the workspace, we fit the same logistic regression model on the Codecademy U training data and made predictions for the test data. Y-test contains the true classes, and Y-pred contains the predicted classes. Create and print a confusion matrix for this data. How many incorrect classifications were there? False positives or false negatives? Accuracy, recall, precision, F1 score. Once we have a confusion matrix, there are a few different statistics we can use to summarize the 4 values in the matrix. These include accuracy, precision, recall, and F1 score. We won't go into much detail about these metrics here, but a quick summary is shown below. T equals true, F equals false, P equals positive, N equals negative. For all of these metrics, a value closer to 1 is better, and closer to 0 is worse. Accuracy equals TP plus TN, TP plus FP plus TN plus FN. Precision equals TP over TP plus FP. Recall, the abbreviations are a little confusing here. So again, once we have a confusion matrix, there are a few different statistics we can use to summarize the 4 values in the matrix. These include accuracy, precision, recall, and F1 score. We won't go into much detail about these metrics here, but a quick summary is shown below. T is true, F is false, P is positive, N is negative. For all of these metrics, a value closer to 1 is better, and closer to 0 is worse. So accuracy, true positive plus true negative divided by true positive plus false positive plus true negative plus false negative. That's the accuracy. Precision equals true positive divided by true positive plus false positive. That's the precision. Recall equals true positive divided by true positive plus false negative. That's the recall. And F1 score is the weighted average of precision and recall. In SciKit-Learn, we can calculate these metrics as follows. Accuracy from SciKit-Learn.metrics, import accuracy score, print accuracy score, y true, y pred, output 0.7. Precision from SciKit-Learn.metrics, import precision score, print precision score, y true, y pred, output 0.67. Recall from SciKit-Learn.metrics, import recall score, print recall score, y true, y pred. F1 score from SciKit-Learn.metrics, import F1 score, print F1 score, y true, y pred, output 0.73. In the workspace, we've fit the same logistic regression model on the Codecademy U training data and made predictions for the test data. Y-pred contains the predicted classes, and Y-test contains the true classes. Also, note that we've changed the train test split by using a different value for the random state parameter, making the confusion matrix different from the one you saw in the previous exercise. Calculate the accuracy for the model and print it out. Calculate the F1 score for the model and print it out. Misspelled something. Print F1 score. Oh. Nice. Review. Congratulations. You just learned how a logistic regression model works and how to fit one to a data set. Here are some of the things you learned. Logistic regression is used to perform binary classification. Logistic regression is an extension of linear regression where we use a logit link function to fit a sigmoid curve to the data rather than a line. We can use the coefficients from a logistic regression model to estimate the log odds that a data point belongs to the positive class. We can then transform the log odds into a probability. The coefficients of a logistic regression model can be used to estimate relative feature importance. A classification threshold is used to determine the probabilistic cutoff for where a data sample is classified as belonging to a positive or negative class. The default cutoff in SciKit-Learn is 0.5. We can evaluate a logistic regression model using a confusion matrix or summary statistics such as accuracy, precision, recall, and F1 score. Find another dataset for binary classification from Kaggle, or take a look at SciKit-Learn's breast cancer dataset. Use SciKit-Learn to build your own logistic regression model on the data and make predictions. Don't feel like it, sorry. A logistic regression model that predicts if a credit card transaction is fraudulent is trained on a dataset with 4 features. Charge amount, the dollar amount for the charge, international, if the charge is made internationally, and 1 if the charge is made internationally, and 0 if the charge is domestic. Recent purchase, 1 if there was a charge on the account in the last 10 minutes, 0 otherwise. Previous purchase, 1 if a charge at the same vendor was made previously, 0 otherwise. The model's coefficients for each feature are given below. Charge amount, 0.23. International, 0.14. Recent purchase, 0.36. Previous purchase, negative 0.60. Which feature has the greatest impact on a charge's classification, and which feature has the least impact? So previous purchase and international. Correct. In this case, previous purchase has the largest coefficient and international has the smallest. You run a logistic regression model and compare the predicted classifications with your test data set and find the following results. True positives 25, true negatives 36, false positives 5, false negatives 4. What are the accuracy, precision, and recall metrics for this model? Accuracy, you want me to just remember it off the top of my head? I guess you could say, I think accuracy was true, positive. I don't remember them. Okay, let me just guess, make an educated guess. Accuracy, precision, recall. I'm not sure. But I'll say, look, we have 25 true positives. One of them was true positive over true positive minus false positive. So true positives is 25. True positives minus false positives is 20, but 25 over 20, that's incorrect. Maybe it's false positives is 5. Not 100% sure. For some reason, this sticks out to me. Correct accuracy, TP, so true positive plus true negative. So that would be what? 55, 61. So 61 over 61 plus 9, which is 70. 61 over 70 gets you 0.87. Okay. Precision, true positive divided by true positive plus false positive. And recall is true positive divided by true positive plus false negative. You have been studying public transportation in your area for the last few months and have noticed that buses have been late 35% of the time at your stop. Calculate the odds and log odds that a bus will be late. So the odds would be 0.35 over 1 minus 0.35. So that's 0.35 over 0.65, which is about what, like 1/2-ish? Yeah, so it's one of these two. And then log odds would be e to the 0.54 power, which since that's below 1, it's got to be negative. So I believe it's this. Which of the following describes the output of logistic regression? A value between 0 and 1, which indicates the probability of a particular outcome. A Boolean value, either 0 or 1. The output of logistic regression is either 0, indicating the event likely won't happen, or 1, indicating that the outcome will likely occur. Logistic regression models will evaluate a probability of an event occurrence and will compare that against the decision threshold to give a prediction. Which function can we apply to a linear regression equation to solve classification problems? Logic link, exponential, probit, quadratic. Correct. For logistic regression, we use the logic link function. Logistic regression differs from linear regression because the output of a logistic regression model ranges from negative infinity to positive infinity. That's false. They're bound to 0, 1. Which of the following plots shows a sigmoid function? C. Which of the following circumstances would be the best candidate for decreasing the standard classification threshold of a logistic regression model from 0.5? The model that predicts cancer diagnoses where has cancer is the positive class, predicts flight delays where delayed is the positive class, predicts customer conversion on a checkout page where converted, takes credit card fraud or fraudulent. So definitely this. With a lower threshold, we would predict more cancer cases and potentially save more lives, even with more false positives. You have a logistic regression model predicting if a customer will make a purchase or not. After running the predict method, you see the following output: 1, 0, 0, 1, 1. Which of the following matrices could be the result of running .predict probo on the same data set and model? Assume the standard classification threshold of 0.5. So not this, maybe this, not this, not this. Oh wait, false, positive, false, negative. I think that's how it goes. False, positive, false, negative. Or sorry, positive, negative probabilities. Yes. So, or maybe it's negative, positive probabilities. Okay. If I assume that negative, positive, that looks good. Negative, positive, that looks good. Negative, positive, that doesn't look good. So negative, positive, that looks good. Negative, positive, that looks right. Negative, positive, that looks right. No, that doesn't look right. Negative, positive, that looks right. Negative, positive, that looks right. Negative, positive, that doesn't look right either. I'm not sure. Oh, wait. I mean, only one of these. So yeah, let's just be sure we can rule this out, right? If it is positive then negative, then this one would look right. This one would look right. This one would look wrong. And I'm pretty sure it's negative, positive. So we'll rule that out. Now let's deal with this negative, positive probability. So that looks right. Negative, that looks right. Is the negative above 0.5? No. So that looks wrong. Is the negative below 0.5? Yes. Is the negative above 0.5? Yes. Above? Yes. Below? Yes. Below. So that one. You run a logistic regression model and compare the predicted classifications with your test data set and find the following results. True positives 25, true negatives 36, false positives 5, false negatives 4. What will the resulting confusion matrix look like? So I'm pretty sure it's the first one. The true positives and the true negatives. So 25. Confusion matrix has a structure: true negatives, false positives, false negatives, true positives. Yeah, it's okay. So predict credit card fraud. Credit card fraud is one of the leading causes of identity theft. All right, I don't do the projects, so let's move to decision trees. So, decision trees. 1 second. Decision trees are machine learning models that try to find patterns in the features of data points. Take a look at the tree on this page. This tree tries to predict whether a student will get an A on their next test by asking questions like, what is the student's average grade in their class? The decision tree tries to get a better understanding of their chances on the next test. In order to make a classification, this classifier needs a data point with 4 features: the student's average grade in the class, the number of hours the student plans on studying for the test, the number of hours the student plans on sleeping the night before the test, whether or not the student plans on cheating. For example, let's say that somebody has a B average in the class, studied for more than 3 hours, slept less than 5 hours before the test, and doesn't plan to cheat. If we start at the top of the tree and take the correct path based on that data, we'll arrive at a leaf node that predicts the person will not get an A on the next test. In this course, you learn how to create a tree like this. Let me reread that just to let it sink in. So, decision trees are machine learning models that try to find patterns in the features of data points. Take a look at the tree on this page. This tree tries to predict whether a student will get an A on their next test by asking questions like, what is the student's average grade in the class? The decision tree tries to get a better understanding of their chances on the next test. In order to make a classification, this classifier needs a data point with 4 features: the student's average grade in the class, the number of hours the student plans on studying for the test, the number of hours the student plans on sleeping the night before the test, whether or not the student plans on cheating. For example, let's say that somebody has a B average in the class, studied more than 3 hours, slept less than 5 hours before the test, and doesn't plan to cheat. Where am I? If we start at the top of the tree and take the correct path based on the data, we'll arrive at a leaf node that predicts the person will not get an A on the next test. In this course, you'll learn how to create a tree like this. Play around with the applet on this page. Fill in the values. At the top of the page, see which leaf node and therefore classification the data point ends up at. So what's our current average? It's A. How many hours will we sleep? Greater than 8. Let's do between 5 and 8, right? How many hours do you plan on studying? Less than 3? Uh-oh. Let's bump it up to more than 3. What if we do less than 3 and we cheat? Prediction, no. Interesting. So if you have an A, this is my confusion though. The plan to cheat is cut off from A or B. Plan to cheat seems like it's only an option if you have a C. And if I have a D and I sleep a lot and I study a lot and I cheat, then it's still no. Interesting. What if I do B? So only a student who gets C's would plan to cheat. It's interesting. Making decision trees. If we're given this magic tree, it seems relatively easy to make classifications. But how do these trees get created in the first place? Decision trees are supervised machine learning models, which means that they're created from a training set of labeled data. Creating the tree is where the learning in machine learning happens. Take a look at the GIF on this page. We begin with every point in the training set at the top of the tree. These training points have labels. The red points represent students that didn't get an A on a test, and the green points represent students that did get an A on a test. We then decide to split the data into smaller groups based on a feature. For example, that feature could be something like their average grade in the class. Students with an A average would go into one set, students with a B average would go into another subset, and so on. Once we have these subsets, we repeat the process. We split the data in each subset again on a different feature. Eventually, we reach a point where we decide to stop splitting the data into smaller groups. We've reached a leaf of the tree. We can now count up the labels of the data in that leaf. If an unlabeled point reaches that leaf, it will be classified as the majority label. We can now make a tree, but how do we know which features to split the data set with? After all, we started by splitting the data based on the number of hours they slept the night before the test. If we did that, we'd end up with a very different tree that would produce very different results. How do we know which tree is best? We'll tackle this question soon. Cars. In this lesson, we'll create a decision tree built off a data set about cars. When considering buying a car, what factors go into making that decision? Each car can fall into 4 different classes, which represent how satisfied someone would be with purchasing the car. Unac is unacceptable, ac is acceptable, good, V good. Each car has 6 features. The price of the car, which can be V high, high, medium, or low. The cost of maintaining the car, which can be V high, high, medium, or low. The number of doors, which can be 2, 3, 4, 5 more. The number of people the car can hold, which can be 2, 4, or more. The size of the trunk, which can be small, medium, or big. The safety rating of the car, which can be low, medium, or high. We've imported a data set of cars behind the scenes and created a decision tree using that data. In this lesson, you'll learn how to build that tree yourself, but for now, let's see what the tree can do. Create a variable named car. We're going to be feeding car into tree. The decision tree we've made behind the scenes. Car should be a list of 6 items, 1 value for each feature. Try to make is a car that you think would have the label V good, and see if the decision tree agrees with you. Make sure your features are in the order listed above. So the price of a car can be very high. Let's do high. Cost of maintaining the car, which can be medium. Number of doors, let's do 4. Number of people the car can hold, let's do 4. The size of the trunk, let's do medium. The safety rating of the car, which can be low, medium, or high, it's too high. We've imported a data set of cars, so try to make sure a car you think will have the label V good. Make sure your features are in the order listed above. Okay. Call classifying using car. Print the result. foreign tree. Acceptable. Gini impurity. Consider the two trees below. Which tree would be more useful as a model that tries to predict whether someone would get an A in a class? Hours studied greater than or equal to 3. Less than 3. Hours studied greater than or equal to 3. Less than 3. So which would be more useful as a model that tries to predict whether someone would get an A in a class? I mean, I guess this first one, right? Because just because you study more than 3 hours doesn't mean you're definitely going to pass. Let's say you use the top tree. You'll end up at a leaf node where the label is up for debate. Oh, I see. We want it to be binary. The training data has labels from both classes. If you use the bottom tree, you'll end up at a leaf node where there's only one type of label. There's no debate at all. We'd be much more confident about our classification if we use the bottom tree. This idea can be quantified by calculating the Gini impurity of a set of data points. To find the Gini impurity, start at 1 and subtract the squared percentage of each label in the set. For example, if a dataset had 3 items of class A and 1 item of class B, the Gini impurity of the set would be 1 minus 3/4 squared minus 1/4 squared equals 0.375. If a dataset has only one class, you'd end up with a Gini impurity of 0. The lower the impurity, the better the decision tree. Let's find the Gini impurity of the set of labels we've given you. Let's start by creating a variable named impurity and set it to 1. We now want to count up how many times every unique label is in the data set. Python's counter object can do this quickly. For example, given the code list AAB, counts equals counter list would result in a counts storing this object. Okay, so create a counter object of labels, items named label counts. Print label counts to see if it matches. So unac 2, ac 2, good 2. Let's find the probability of each label given the data set. Loop through each label in label counts. Create a variable named probability of label. Probability of label set equal to the label count divided by equals the label count divided by total number of labels in the data set. For every label, the count associated with that label can be found at label counts label. We can find the total number of labels in the data set with length labels. We now want to take probability of label, square it, and subtract it from impurity. Inside the for loop, subtract probability of label squared from impurity. In Python, you can square x by using x squared. So purity minus equals outside the for loop, print impurity. Test out some of the other labels that we've given you by uncommenting them. Which one do you expect to have the lowest impurity? Definitely the third one. In the next exercise, we'll put all of your code into a function. If you want to challenge, try creating the function yourself. Ours is named Ginny, takes label as a parameter, returns impurity. I'd rather just learn. Information gain. We know that we want to end up with leaves with a low Ginny impurity, but we still need to figure out which features to split on in order to achieve this. For example, is it better if we split our data set of students based on how much sleep they got or how much time they spent studying? To answer this question, we can calculate the information gain of splitting the data on a certain feature. Information gain measures difference in the impurity of the data before and after the split. For example, let's say you had a data set with an impurity of 0.5. After splitting the data based on a feature, you end up with 3 groups with impurities 0, 0.375, and 0. The information gain of splitting the data in that way is 0.5 minus 0 minus 0.375 minus 0 equals 0.125. Not bad. By splitting the data in that way, we've gained some information about how the data is structured. The data sets after the split are purer than they were before the split. The higher the information gain, the better. If information gain is 0, then splitting the data on that feature was useless. Unfortunately, right now, it's possible for information gain to be negative. In the next exercise, we'll calculate weighted information gain to fix that problem. We've given you a set of labels named unsplit labels, and 2 different ways of splitting those labels into smaller subsets. Let's calculate the information gain of splitting the labels in this way. At the bottom of your code, begin by creating a variable named info gain. Info gain should start at the Ginny impurity of the unsplit labels. We now want to subtract the impurity of each subset. Just let this sink into my brain, right? So Ginny impurities variable is def Ginny dataset, impurity equals 1, label counts equals counter dataset. For label and label counts, prob of label equals label counts label divided by length of dataset. Impurity minus equals prob of label squared, return impurity. And again, we're calculating the information gain, splitting the data on a certain feature. Information gain measures difference in the impurity of the data before and after the split. For example, let's say you had a data set with an impurity of 0.5. After splitting the data based on a feature, you end up with 3 groups with impurities. These, the information gain of splitting the data in this way is that. Not bad. Okay. So we now want to subtract the impurity of each subset in split labels 1 from info gain. Loop through every subset in split labels 1. So for subset we want to change the value of info for every subset. Calculate the Ginny impurity and subtract it from info gain. Outside your loop, print info gain. We've given you a second way to split the data. Instead of looping through the subsets in split labels 1, loop through the subsets in split labels 2. Which split resulted in more information gain. Once again, in the next exercise, we'll put the code you wrote into a function named information gain that takes unsplit labels and split labels as parameters. So we had more information gain with split labels 1, which makes sense. Does it make sense actually? Weighted information gain. We're not quite done calculating the information gain of a set of objects. The sizes of the subset that get created after the split are important too. For example, the image below shows 2 sets with the same impurity. Which set would you rather have in your decision tree? Impurity equals 0 versus impurity equals 0. Both of these sets are perfectly pure, but the purity of the second set is much more meaningful. Because there are so many items in the second set, you can be confident that whatever we did to produce this set wasn't an accident. It might be helpful to think about the inverse as well. Consider these two sets with the same impurity. Both of these sets are completely impure. However, that impurity is much more meaningful in the set with more instances. We know that we are going to have to do a lot more work in order to completely separate the two classes. Meanwhile, the impurity of the set with two items isn't as important. We know that we'll only need to split the set one more time in order to make two pure sets. Let's modify the formula for information gain to reflect the fact that the size of the set is relevant. Instead of simply subtracting the impurity of each set, we'll subtract the weighted impurity of each of the split sets. If the data before the split contained 20 items, and one of the resulting splits contained 2 items, then the weighted impurity of that subset would be 2 divided by 20 times impurity. We're lowering the importance of the impurity of sets with few elements. So impurity equals 0.5. Then we split it up. Impurity equals 0.5. The weight equals 2 over 10. Impurity equals 0.48. Weight equals 5 over 10. And impurity equals 0.44. Weight equals 3 over 10. Weight information gain equals 0.5 minus 2 over 10 times 0.5 minus 5 over 10 times 0.48 minus 3 over 10 times 0.44. So our total weight information gain is 0.026. Now that we can calculate the information gain using weighted impurity, let's do that for every possible feature. If we do this, we can find the best feature to split the data on. Let's update the information gain function to make it calculate weighted information gain. When subtracting the impurity of a subset from info gain, first multiply the impurity by the correct percentage. So this is our information gain function. We've taken starting labels and split labels. Info gain equals the Gini impurity of the starting labels for subset and split labels. Multiply Gini subset by the correct percentage below. Info gain minus equals Gini subset. So it would be length of the subset over okay. So the impurity is the impurity, and the weight is calculated by taking the total number of values and dividing it by the original of the, so the total number of values in the subset, and dividing it by the length of the original subset. So length of subset, so Gini subset times update the line of code information gain we subtract from info gain, multiply Gini subset by length of subset divided by length of starting labels. We've given you a split function along with 10 cars and the car labels associated with those cars after your information gain function. Call split using cars. Car labels. And 3. As a parameter, this will split the data based on the third index. That feature was the number of people the car could hold. Split returns two lists. Create two variables named split data and split labels. I think I can just do, I think I can do that. take a look. Let's make sure, yeah. Python functions can return more than one value. When this happens, you can do something like this. Do this with your split function. Take a look at what these variables are. Begin by printing split data. It's kind of hard to tell what's going on there. There are so many lists of lists. Try printing the length of split data. What do you think this is telling you? Also try printing split data 0. What do you notice about the items at index 3 of all these lists? Remember when we called split, we used 3 as the split index. Try printing split data 1. What do you notice about the items at index 3 of these lists? So it's a little hard to read. So when we call split data, this is what we get. The length of it is 3. Split data 0 is this. Split data 1 is this. So I think it's telling us that it's split it 3 ways, and each split is like a corresponding box. We now know, what do you notice about the items at index 3 of these lists? Well, I realized that they remain the same. So we now know that split data contains the cars split into different subsets. Split labels contains the labels of those cars split into different subsets. Use those split labels to find the information gain of splitting on index 3. Remember, the information gain function takes a list of labels before the split, car labels, and a list of the subsets of labels after the split, split labels. Call this function and print the result. How do we do when we split the function at index 3? So again, we know that split data contains the cars split into different subsets. Split labels contains the labels of those cars split into different subsets, right? Use those split labels to find the information gain of splitting on index 3. Remember, the information gain function takes a list of labels before the split, car labels, and a list of these subsets of labels after the split, split labels. Call this function and print the result. See that we got an information gain of about 3, or 30%-ish. We found the information gain when splitting on feature 3. Let's do the same for every possible feature. Loop through all the features of our data to find the best one to split on. So for So it looks like, yeah, this feature 3, produces the most information gain. Recursive tree building. Now that we can find the best feature to split the data set, we can repeat this process again and again to create the full tree. This is a recursive algorithm. We start with every data point from the training set, find the best feature to split the data based on that feature, and then recursively repeat the process again on each subset that was created from the split. We'll stop the recursion when we can no longer find a feature that results in any information gain. In other words, we want to create a leaf of the tree when we can't find a way to split the data that makes pure subsets. The leaf should keep track of the classes of the data points from the training set that ended up in the leaf. In our implementation, we'll use a counter object to keep track of the counts of labels. We'll use these counts to make predictions about new data that we give the tree. I'm going to read that again, let it really sink in. Recursive tree building. Now that we can find the best feature to split the data set, we can repeat this process again and again to create the full tree. This is a recursive algorithm. We start with every data point from the training set, find the best feature to split the data based on that feature, and then recursively repeat the process again on each subset that was created from the split. We'll stop the recursion when we can no longer find a feature that results in any information gain. In other words, we want to create a leaf of the tree when we can't find a way to split the data that makes pure subsets. The leaf should keep track of the classes of the data points from the training set that ended up in the leaf. In our implementation, we'll use a counter object to keep track of the counts of labels. We use these counts to make predictions about new data that we give the tree. We've given you the function findBestSplit that takes a set of data points and a set of labels. The function returns the index of the feature that causes the best split and the information gain caused by that split. For now, at the bottom of your code, call this function using car data and car labels. So as parameters, and store the values in variables named best feature and best gain. Print those two variables. So the best feature was feature 3 and the best gain was its gain. What was the best feature to split on? What was the information gain? Let's create a function called buildTree. That takes data and labels as parameters. Move your call of findBestSplit inside the function, but change the parameters from car data and car labels to data and labels. If best gain is 0, return counter labels. We've reached the base case. There's no way to gain any more information, so we want to create a leaf. After the if statement, we want to start working on the recursive case. In the recursive case, we want to split the data into subsets using the best feature. And then recursively call the buildTree function on those subsets to create subtrees. Finally, we want to return a list of all those trees. Let's begin by splitting the data. You can do this by using the split function, which takes 3 parameters: the data, the labels, and the index of the feature you want to split on. Store the result of the split function, 2 variables named data subsets and label subsets. For now, return data subsets to the bottom of your function. before that final return statement, create an empty list named branches. This will store all of the subtrees we're about to make from our recursive calls. We now want to loop through all of the subsets of data and labels. Set up your for loop like this. Inside the for loop called build tree, using data subsets I, and label subsets I as parameters, and append the result to branches. Finally, outside the for loop, return branches instead of data subsets. Let's test your function at the bottom of your code. Outside of your function definition called build tree, using car data and car labels as parameters, and store the result in a variable named tree. We've written a function called print tree that will help you visualize the tree, called print tree, using tree as a parameter. So this is our best feature. This is our best gain. We're splitting, so branch 0, counter unack 4, branch 1, splitting, branch 0, counter good 1, branch 1, counter ack 1, branch 2, counter unack 1, branch 2, splitting, branch 0, counter v good 1, branch 1, counter ack 1, branch 2, counter ack 1. Classifying new data. We can finally use our tree as a classifier. Given a new data point, we start at the top of the tree and follow the path of the tree until we hit a leaf. Once we get to a leaf, we'll use the classes of the points from the training set to make a classification. We've slightly changed the way our build tree function works. Instead of returning a list of branches or a counter object, the build tree function now returns a leaf object or an internal node object. We'll explain how to use these objects in the instructions. Let's write a function that will use our tree to classify new points. We've created a tree named tree. Using a lot of car data, use the print tree function with tree as a parameter to see it. Notice that the tree now knows which feature was used to split the data. This new information is contained in the leaf and internal node classes. This will come in handy when we write our classify function. Comment out printing the tree once you get a sense of how large it is. It's very large. Splitting on estimated safety. Branch high, splitting on person capacity. Branch 2, counter unack 174. So a lot of stuff. And we'll comment it out. Let's start writing the classify function. Classify should take a data point and tree as a parameter. The first thing classify should do is check to see if we're at a leaf. Check to see if tree is a leaf by using the isInstance function. So if for example, isInstance so be true if A is a list, you should check if tree is a leaf. If we found a leaf, that means we want to return the label with the highest count. The label counts are stored in tree.labels. You could find the label with the largest count by using a for loop or by using this rather complicated line of code. Return max tree.labels.items. Key equals operator the item getter 1 0. Your statement should look like this if this instance tree. If we're not at a leaf, we want to print the branch that corresponds to our data point. For example, if we're splitting on index 0 and our data point is medium, low, 4, 2, big, low, we want to find the branch that contains all of the points with medium at index 0. So again, if we're not at a leaf, so we want to find the branch that corresponds to our data point. For example, if we're splitting at index 0, our data point is medium, low, 4, 2, big, low, we want to find the branch that corresponds, that contains all of the points with medium at index 0. To start, let's find data points, value of the feature we're looking for. If data point were the example above, and the feature we're interested in is 0, this would be medium. Outside the if statement, create a variable named value. And set it equal to data point tree.feature. Tree feature contains the index of the feature that we're splitting on, so data point tree feature is the value at that index. To help us check the code, return value. Start by deleting return value. Let's now loop through all of the branches in the tree to find the one that has the data points with value at the correct index. Your loop should look like this for branch tree.branches. Next, inside the loop, check to see if branch.value is equal to value. If it is, we found the branch that we're looking for. We want to now recursively call classify on that branch. We know that one of these branches will be the one we're looking for, so we know that this return statement will happen once. Finally, outside of your function, call classify using test point and tree as parameters. Print the results. You should see a classification for this new point. Unack. Decision trees in SciKit-Learn. Nice work. You've written a decision tree from scratch that is able to classify new points. Let's take a look at how the Python library SciKit-Learn implements decision trees. The sklearn.tree module contains the decision tree classifier class. To create a decision tree classifier object, call the constructor. Next, we want to create the tree based on our training data. To do this, we'll use the .fit method. .fit takes a list of data points followed by a list of labels associated with that data. Note that when we built our tree from scratch, our data points contain strings like v-high or 5 more. When creating the tree using scikit-learn, it's a good idea to map those strings to numbers. For example, for the first feature representing the price of the car, low would map to 1, medium would map to 2, and so on. Classifier.fit training data, training labels. Finally, once we've made our tree, just real quick, I'm trying to remember, is that called imputation? Imputation is a technique for replacing missing data with some substitute value to retain most of the data. So that's not what it's called. I'm trying to remember what it's called when you change a categorical variable to a numerical variable. What is it? Label encoding. So back here, so for example, for the first feature representing the price of the car, low would map to 1, medium would map to 2, and so on. Classifier.fit training data, training labels. Finally, once we've made our tree, we can use it to classify new data points. The predict method takes an array of data points and will return an array of classifications for those data points. If you've split your data into a test set, you can find the accuracy of the model by calling the .score method using the test data and the test labels as parameters. Print classifier.score test data test labels. .score returns the percentage of data points from the test set that it classified correctly. We've imported the full car data set and split it into a training and test set. We've also mapped the features that were strings like vgood to numbers. Print training points 0. So see the first car in your training set. So 4.0, 3.0, 4.0, 2.0, 1.0, 2.0 ACK. Create a decision tree classifier, name it classifier. Build the tree using the training data by calling the .fit method. Test the decision tree on the testing set and print the results. Classifier.predict. Print the results of the .score method. Pretty good, pretty good. Decision tree limitations. Now that we have an understanding of how decision trees are created and used, let's talk about some of their limitations. One problem with the way we're currently making our decision trees is that our trees aren't always globally optimal. This means that there might be a better tree out there somewhere that produces better results. But wait, why did we go through all that work of finding information gain if it's not producing the best possible tree? Our current strategy of creating trees is greedy. We assume that the best way to create a tree is to find the feature that will result in the largest information gain right now and split on that feature. We never consider the ramifications of that split further down the tree. It's possible that if we split on a suboptimal feature right now, we would find even better splits later on. Unfortunately, finding a globally optimal tree is an extremely difficult task, and finding a tree using our greedy approach is a reasonable substitute. Another problem with our trees is that they potentially overfit the data. This means that the structure of the tree is too dependent on the training data and doesn't accurately represent the way the data in the real world looks like. In general, larger trees tend to overfit the data more. As the tree gets bigger, it becomes more tuned to the training data, and it loses a more generalized understanding of the real world data. One way to solve this problem is to prune the tree. The goal of pruning is to shrink the size of the tree. There are a few different pruning strategies, and we won't go into the details of them here. SciKit-Learn currently doesn't prune the tree by default. However, we can dig into the code a bit to prune it ourselves. We've created a decision tree classifier for you and printed its accuracy. Let's see how big the tree is. If your classifier is named classifier, you can find the depth of the tree by printing classifier.tree.maxDepth. Print the depth of classifier's decision tree. Take note of the accuracy as well. So the accuracy is high, its max depth is 12. Classifier should have a depth of 12. Let's prune it. When you create classifiers, set the parameter max depth equal to 12. So create classifier, random state equals 0. Set the max depth equal to 11. What is the accuracy of the classifier after pruning the tree from size 12 to size 11? Accuracy goes up, and now we have a max depth of 11. Cool. Review. Great work. In this lesson, you learned how to create decision trees and use them to make classifications. Here are some of the major takeaways. Good decision trees have pure leaves. A leaf is pure if all of the data points in that class have the same label. Decision trees are created using a greedy algorithm that prioritizes finding the feature that results in the largest information gain when splitting the data using that feature. Creating an optimal decision tree is difficult. The greedy algorithm doesn't always find the globally optimal tree. Decision trees often suffer from overfitting. Making the tree small by pruning helps to generalize the tree so it is more accurate on data in the real world. Why is the algorithm used to construct decision trees considered a greedy algorithm? The algorithm doesn't look ahead. It chooses to split the data based on the best possible feature given the current data set. Correct, it's greedy because it does what is best right now without thinking about the future. How would the following decision tree classify the point 2, 1, 1, 0? So split at index 2, so 1, split at index 1, 1, split at index 3, 0, so C. Correct, the value of the second index is 1, the value of the first index is 1, the value of the third index is 0. What does SciKit-Learn's decision tree classifiers .fit method do? The fit method returns the accuracy, no. Fit method creates a decision tree classifier object. Fit method creates the tree according to the training data and training labels. Creates a random forest. Yeah, it's this. This is where the tree gets created based on the training set. What is the condition for the base case of the recursive algorithm that creates a decision tree? We've reached the base case when splitting on one feature results in information gain greater than 0. We've reached the base case when splitting on every feature results in information gain greater than 0. We've reached the base case when splitting on one feature results in no information gain. We've reached the base case when splitting on every feature results in no information gain. If we don't gain any information by splitting the data, we should create a leaf. What do you have to consider when calculating weighted information gain as opposed to unweighted information gain? The Gini impurity of each subset, how many times you've already split the data, the relative sizes of each subset after the split, the index of the feature that was used to split the data. And again, the question is, what do you have to consider when calculating the weighted information gain as opposed to the unweighted information gain? I believe it's the Gini impurity. No. Calculating the Gini impurity of each subset is necessary when calculating both weighted and unweighted information gain. Yeah, I knew that. The relative sizes of each subset after the split. What do the internal nodes of a decision tree represent? Sorry, I'm just saying when I said, yeah, whatever, it's like I was annoyed that I got it wrong, but it's like, it's fine, I'm learning. What do the internal nodes of a decision tree represent? Decision trees, okay, an internal node represents the predicted class of an unlabeled point that reaches that node. An internal node represents the Gini impurity of a set of data. An internal node represents which feature to split the data on. So it's the predicted class. Oh, unlabeled data is classified when it reaches the leaves of the tree. An internal node represents which feature to split the data on. Not doing good. Which data set has the largest Gini impurity? A set of 20 objects. 5 have label A, 5 have label B, 5 have label C, 5 have label D. Set of 20 objects, 10 have label A and 10 have label B. Set of 100 objects. So it's obviously one of these, right? I believe that the impurity goes up. How do we calculate the impurity again? Gini impurity. I think it's 1 minus 5 over 10. I'm trying to remember if it's better to have. So, okay, which one would I consider more impure, right? If I have a glass of water or let's say I have a cup and half of it is water and half of it is oil. Or if I have a cup with, a quarter of water, a quarter of oil, a quarter of milk, and a quarter of, I don't know, let's just say liquor, right? I would say that that's more impure. Correct. This has an impurity of 0.75. You guess which continent this flag comes from? I don't know, but it's a pretty interesting looking flag. I wonder if that's real. So, random forest. We've seen that decision trees can be powerful, supervised machine learning models. However, they're not without their weaknesses. Decision trees are often prone to overfitting. We've discussed some strategies to minimize this problem, like pruning, but sometimes that isn't enough. We need to find another way to generalize our trees. This is where the concept of a random forest comes in handy. A random forest is an ensemble machine learning technique. A random forest contains many decision trees that all work together to classify new points. When a random forest is asked to classify a new point, the random forest gives that point to each of the decision trees. Each of those trees reports their classification, and the random forest returns the most popular classification. It's like every tree gets a vote, and the most popular classification wins. Some of the trees in the random forest may be overfit, but by making the prediction based on a large number of trees, overfitting will have less of an impact. In this lesson, we'll learn how the trees in a random forest get created. So again, we've seen how decision trees can be powerful supervised machine learning models. However, they're not without their weaknesses. Decision trees are often prone to overfitting. We've discussed some strategies to minimize this problem, like pruning, but sometimes that isn't enough. We need to find another way to generalize our trees. This is where the concept of a random forest comes in handy. A random forest is an ensemble machine learning technique. A random forest contains many decision trees that all work together to classify new points. When a random forest is asked to classify a new point, the random forest gives that point to each of the decision trees. Each of those trees reports their classification, and the random forest returns the most popular classification. It's like every tree gets a vote, and the most popular classification wins. Some of the trees in the random forest may be overfit, but by making the prediction based on a large number of trees, overfitting will have less of an impact. In this lesson, we'll learn how the trees in a random forest get created. So, will I get an A on the next test? Hours slept is greater than or equal to 8. Plans to cheat? No. Hours studied is less than or equal to 3. Average grade is a B. Yes, 6. No, 5. Final prediction, yes. Bagging. You might be wondering how the trees in the random forest get created. After all, right now, our algorithm for creating a decision tree is deterministic. Given a training set, the same tree will be made every time. Random forests create different trees using a process known as bagging. Every time a decision tree is made, it is created using a different subset of the points in the training set. For example, if our training set had 1,000 rows in it, we could make a decision tree by picking 100 of those rows at random to build the tree. This way, every tree is different, but all trees will still be created from a portion of the training data. One thing to note is that when we're randomly selecting these 100 rows, we're doing so with replacement. Picture putting all 100 rows in a bag and reaching in and grabbing one row at random. After writing down what row we picked, we put that row back in our bag. This means that when we're picking our 100 random rows, we could pick the same row more than once. In fact, it's very unlikely, but all 100 randomly picked rows could all be the same row. One thing to note is that when we're randomly selecting 100 rows, we're doing so with replacement. Picture putting 100 rows in a bag and reaching in and grabbing one row at random. After writing down what row we picked, we put that row back in our bag. This means that when we're picking our 100 random rows, we could pick the same row more than once. In fact, it's very unlikely, but all 100 randomly picked rows could all be the same row. Because we're picking these rows with replacement, there's no need to shrink our bag training set from 1,000 rows to 100. We can pick 1,000 rows at random, and because we can get the same row more than once, we'll still end up with a unique data set. Let's implement bagging. We'll be using the data set of cars that we used in our decision tree lesson. Start by creating a tree using all of the data we've given you. Create a variable named tree and set it equal to the build tree function. Using car data and car labels as the parameters. Then call print tree using tree as a parameter. Scroll up to the top to see the root of the tree, which features used to split the data at the root. Branch high person capacity. For now, comment out printing the tree. Let's now implement bagging. The original data set has 1,000 items in it. We want to randomly select a subset of those with replacement. Create a list named indices that contains 1,000 random numbers between 0 and 1,000. We'll use this list to remember the 1,000 cars and the 1,000 labels that we're going to build a tree with. You can use either a for loop or list comprehension to make this list. To get a random number between 0 and 1,000, use random.randint 0,999. So indices equals how would you do this comprehension with this? So I guess it would be num in wait, let me try something. It's gonna work. would you do with list comprehension? So something for I in range 1000. If you chose to do a for loop, your code might look something like this. Or we could do indices equals rand int 0 999 for I range 1000. I'm gonna go with that just so we don't introduce any problems. Random int dot, so random.randint 0 through 999 for I in range 1000. Create two new lists named dataset and data subset. These two lists should contain the cars and labels found at each index and indices. Create two new lists named data subset and labels subset. These two lists contain the cars and labels found at each index. So data subset equals car data index for index and indices. And label subset would be car labels index for index and indices. Is that right? Nice. Create a tree named subset tree. Print subset tree using the print tree function. Which feature is used to split the data at the root? Predict counter on ACK. Is it a different feature than the feature that split the tree that was created using all of the data? Yes. You've just created a new tree from the training set. If you used 1,000 different indices, you'd get another different tree. You could now create a random forest by creating multiple different trees. Bagging features. We're now making trees based on different random subsets of our initial subset, but we can continue to add variety to the ways our trees are created by changing the features that we use. Recall that for our car dataset, the original features were the following: the price of the car, the cost of maintenance, the number of doors, the number of people the car can hold, the size of the trunk, the safety rating. Right now, when we create a decision tree, we look at every one of those features and choose to split the data based on the feature that produces the most information gain. We could change how the tree is created by only allowing a subset of those features to be considered at each split. For example, when finding which feature to split the data on the first time, we might randomly choose to only consider the price of the car, the number of doors, and the safety rating. After splitting the data on the best feature from that subset, we'll likely want to split again. For this next split, we'll randomly select 3 features again to consider. This time those features might be the cost of maintenance, the number of doors, and the size of the trunk. We'll continue this process until the tree is complete. One question to consider is how to choose the number of features to randomly select. Why do we choose 3 in this example? A good rule of thumb is to randomly select the square root of the total number of features. Our car dataset doesn't have a lot of features, so in this example, it's difficult to follow this rule, but if we had a dataset with 25 features, we'd want to randomly select 5 features to consider at every split point. I'm going to go ahead and read this again. So bagging features. We're now making trees based on different random subsets of our initial dataset, but we can continue to add variety to the ways our trees are created by changing the features that we use. Recall that for our car dataset, the original features were the following: the price of the car, the cost of maintenance, the number of doors, the number of people the car can hold, the size of the trunk, the safety rating. Right now, when we create a decision tree, we look at every one of those features and choose to split the data based on the feature that produces the most information gain. We could change how the tree is created by only allowing a subset of those features to be considered at each split. For example, when finding which feature to split the data on the first time, we might randomly choose to only consider the price of the car, the number of doors, and the safety rating. After splitting the data on the best feature from that subset, we'll likely want to split again. For this next split, we'll randomly select 3 features again to consider. This time, those features might be the cost of maintenance, the number of doors, and the size of the trunk. We'll continue this process until the tree is complete. One question to consider is how to choose the number of features to randomly select. Why do we choose 3 in this example? A good rule of thumb is to randomly select the square root of the total number of features. Our car dataset doesn't have a lot of features, so in this example, okay, and so on. If you've given you access to the code that finds the best feature to split on, def find best split, dataset labels best gain equals 0, best feature equals 0. Right now, it considers all possible features. We're going to want to change that. For now, let's see what the best feature to split the dataset is. At the bottom of your code, call find best split. Using data subset, labels subset as parameters, and print the results. So feature 3, we now want to modify our find best split function to only consider a subset of the features. We want to pick 3 features without replacement. The random.choice function found in Python's NumPy module can help us do this. Random.choice returns a list of values between 0 and the first parameter. The size of the list is determined by the second parameter, and we can choose without replacement by setting replace equals false. For example, the following code would choose 10 unique numbers between 0 and 100 exclusive and put them in a list. List equals numpy.random.choice, 110, replace equals false. Inside find best split, create a list named features. That contains 3 numbers between 0 and length of dataset. np.random.choice. It says 3 numbers between 0 and length of dataset. 0, 3. Instead of looping through feature in range length of dataset, loop through feature and features. Now that we've implemented, feature should be np.random.choice 3. I see. 3 numbers. Oh, I see. Wait, no. Choose 10 unique numbers between 0 and 100. Contains 3 numbers between 0 and length of dataset. That's confusing me. Like, I thought this number was acting as the range because it says, and this number was acting as the number to pull. It says 10 unique numbers between 0 and 100 exclusive. So if we want to find 3 numbers between 0 and length dataset, I'm confused. Whatever. The best split should now be at index 4 with information gained about. That's what I had it at. Hold on. Did I have a typo or something? So this is, can I flag this? Whatever. Okay, so now what's the issue? Features equals np.random.choice len dataset 0, comma 3, comma replace. Oh, I have two of these. But this is still wrong. So now that we've implemented feature bagging, what is the best index to use as the split index? Index 4. Classify. Now that we can make different decision trees, it's time to plant a whole forest. Let's say we make different 8 trees. Somebody needs to get their English game up. I'm sorry, but it's just the truth. Let's say we make 8 different trees using bagging and feature bagging. We can now take a new unlabeled point, give that point to each tree in the forest, and count the number of times different labels are predicted. The trees give us their votes, and the label that is predicted most often will be our final classification. For example, if we gave our random forest of 8 trees a new data point, we might get the following results. V good, V good, good, V good, ac, V good, good, V good. Since the most commonly predicted classification was V good, this would be the random forest final classification. Let's write some code that can classify an unlabeled point again. Now that we can make different decision trees, it's time to plant a whole forest. Let's say we make 8 different trees using bagging and feature bagging. We can now take a new unlabeled point, give that point to each tree in the forest, and count the number of times different labels are predicted. The trees give us their votes, and the label that is predicted most often will be our final classification. For example, if we gave our random forest of 8 trees a new data point, we might get the following results. Since the most commonly predicted classification was V good, this would be the random forest final classification. Let's write some code that can classify an unlabeled point. At the top of your code, we've included a new unlabeled car named unlabeled point that we want to classify. We've also created a tree named subset tree that was created using bagging and feature bagging. Let's see how that tree classifies this point. Print the results of classify using unlabeled point and subset tree. Ac. That's the prediction using one tree. Let's make 20 trees and record the prediction of each one. Take all of your code between creating indices and the print statement you just wrote and put it in a for loop. That happens 20 times. Above your for loop, create a variable named predictions. And set it equal to an empty list. Inside your for loop, instead of printing the prediction, use .append. To add it to predictions, finally after your loop, print predictions. Bunch of acts. Now we have a list of 20 predictions. Let's find the most common one. You can find the most common element in a list by using this line of code. Max predictions key, predictions count. Outside of your for loop, store the most common element in a variable named final prediction. And print that variable. Test set. We're now able to create a random forest, but how accurate is it compared to a single decision tree? To answer this question, we've split our data into a training set and test set. By building our models using the training set and testing on every data point in the test set, we can calculate the accuracy of both a single decision tree and a random forest. So again, we're now able to create a random forest, but how accurate is it compared to a single decision tree? To answer this question, we split our data into a training set and test set. By building our models using the training set and testing on every data point in the test set, we can calculate the accuracy of both a single decision tree and a random forest. We've given you code that calculates the accuracy of a single tree. This tree was made without using any of the bagging techniques we just learned. We created the tree by using every row from the training set once and considered every feature when splitting the data rather than a random subset. Let's also calculate the accuracy of a random forest and see how it compares. Begin by taking a look at the code we've given you. We've created a single tree using the training data, looped through every point in the test set, counted the number of points the tree classified correctly, and reported the percentage of correctly classified points. This percentage is known as the accuracy of the model. Run the code to see the accuracy of the single decision tree. Right below where tree is created, create a random forest named forest using our make random forest. Function. This function takes 3 parameters: the number of trees in the forest, the training data, and the training labels. It returns a list of trees. Create a random forest with 40 trees using training data and training labels. You should also create a variable named forest correct and start it at 0. This is the variable that will keep track of how many points in the test set the random forest correctly classifies. For every data point in the test set, we want every tree to classify the data point, find the most common classification, and compare that prediction to the true label of the data point. This is very similar to what you did in the previous exercise. To begin, at the end of the for loop, outside the if statement, create an empty list named predictions. Next, loop through every forest, tree, and forest. So was this supposed to go above my if statement? Right below where tree is created, I see. So for forestry and forest, call classify using testing data I. After we loop through every tree in the forest, we now, something went wrong. Name testing is not defined. Classify testing data. After we loop through every tree in the forest, we now want to find the most common prediction and compare it to the true label. The true label can be found using testing labels I. If they're equal, we've correctly classified a point and should add 1 to forest correct. An easy way of finding the most common prediction is by using this line of code. Forest prediction equals max predictions key equals predictions.count. So again, after we loop through every tree in the forest, we now want to find the most common prediction and compare it to the true label. The true label can be found using testing labels I. So forest prediction equals max predictions key equals predictions.count, and now we got the most common prediction compared to the true label. So forest prediction is equal to true label testing labels I. If they're equal, we've correctly classified a point and should add 1 to forest correct. Finally, after looping through all the points in the test set, name forest prediction is not defined. Forest prediction. Oh. Oh goodness. Why am I so bad at spelling this word? Okay, finally, after looping through all of the points in the test set, we want to print out the accuracy of our random forest, divide forest correct by the number of items in the test set, and print the result. So finally, after looping through all the points in the test set, we want to print out the accuracy of our random forest. Divide, so print, wait. This is after the loop. How did the random forest do compared to the single decision tree? Better, for sure. Random forest and SciKit-Learn. You now have the ability to make a random forest using your own decision trees. However, SciKit-Learn has a random forest classifier class that will do all of this work for you. Random forest classifier is in the SciKit-Learn.ensemble module. Random forest classifier works almost identically to decision tree classifier. The .fit, .predict, and .score methods work in the exact same way. When creating a random forest classifier, you can choose how many trees to include in the random forest by using the n-estimators parameter like this. Classifier equals random forest classifier, n-estimators equals 100. We now have a very powerful machine learning model that is fairly resistant to overfitting. Create a random forest classifier named classifier. When you create it, pass 2 parameters to the constructor. N-estimator should be 2000. Random state equals 0. That's an element of randomness when creating random forest thanks to bagging. Setting the random state to 0 will help us test your code. Train the forest using the training data by calling the fit method. Training points. Training labels. Test the random forest on the testing set and print the results. Pretty accurate. Review. Nice work. Here are some of the major takeaways about random forests. A random forest is an ensemble machine learning model. It makes a classification by aggregating the classifications of many decision trees. Random forests are used to avoid overfitting. By aggregating the classification of multiple trees, having overfitted trees in a random forest is less impactful. Every decision tree in a random forest is created by using a different subset of data points from the training set. Those data points are chosen at random with replacement, which means a single data point can be chosen more than once. This process is known as bagging. When creating a tree in a random forest, a randomly selected subset of features are considered as candidates for the best splitting feature. If your dataset has n features, it is common practice to randomly select the square root of n features. How does a random forest use the classifications from its decision trees to make a final prediction? A random forest uses a random classification from its decision trees. The average is the most common classification. Why is a random forest considered an ensemble machine learning model? Makes classification by aggregating the classification of multiple decision trees, meant to be used with other machine learning models. Makes classification by random picking an ensemble machine learning. What problem with decision trees do random forests try to minimize? Overfitting. If you have n rows in your training set, how many rows should you randomly select when implementing bagging with replacements? No, because we're selecting rows with replacement, there's no need to decrease the size of your training set. I knew that. Whatever. When creating a random forest classifier from SciKit-Learn, what does the n-estimators parameter represent? The number of trees in the forest, the number of rows to randomly select when implementing bagging, the number of features to consider when implementing feature bagging, The maximum depth of the trees in the forest. I actually don't remember this one, but I think it's the number of trees. Yeah, correctly. If you don't include this parameter, the default is 10. When a tree in a random forest is created, how are the features of the points in the training set used? Features of the points in the training set used. Tree at every point, a split needs to be made. Different subset of features are considered. So what's the question again? So when a tree in a random forest is created, how are the features of the points in the training set used? When constructing the tree, at every point a split needs to be made. A different subset of features are considered. When constructing the tree at every point, a split needs to be made. The first square root of n features are considered. When constructing the tree at every point, a split needs to be made. The same subset of features are considered. When constructing the tree at every point, a split needs to be made. So it's this. Every time you try to find the best feature to split the data on, you randomly select a different subset of features, often of size square root of n. If your data has n features, how many should you consider when implementing feature bagging? This is square root of n. The number can be tuned, but square root of n is a good place to start. What does it mean to implement bagging with replacement? When randomly selecting rows to be in our training set, a row that has already been selected will be replaced by a different row. If there are n rows in our training set, when randomly selecting rows to be in our training set, we randomly replace values in rows to create new data ones. When randomly selecting rows to be in our training set, the same row can be selected more than once. Correct. When selecting with replacement, the same row can be chosen any number of times. Not terrible. Times it pretty early. Predicting income with random forests. So what's left? I'm not going to do the project. So we have advanced classification with evaluation metrics, support vector machines, and naive based classifier. We have in unsupervised learning, we have clustering. And then we have our intro to neural networks, which I've already done this part, but I need to do PyTorch for classification. So really all that's left is learning about evaluation metrics, learning about support vector machines, naive bayes classifier, clustering, and classification with PyTorch. So this is good. Let's keep it pushing. What we doing over here? Doing good. Audio's good. Still streaming, cool. Confusion matrix. When creating a machine learning algorithm capable of making predictions, an important step in the process is to measure the model's predictive power. In this lesson, we will learn how to calculate some of the more common evaluation metrics for classification problems. Remember, in order to calculate these statistics, we need to split our data into a training, validation, and test set before we start fitting our model. Let's say we are fitting a machine learning model to try to predict whether or not an email is spam. We can pass the features of our evaluation set through the trained model and get an output list of the predictions our model makes. When we then compare each of these predictions to the actual labels, there are 4 possible categories that each of the comparisons can fall under. True positive, the algorithm predicted spam and it was spam. True negative, the algorithm predicted not spam and it was not spam. False positive, the algorithm predicted spam and it was not spam. False negative, the algorithm predicted not spam and it was spam. One common way to visualize these values is in a confusion matrix. In a confusion matrix, the predicted classes are represented as columns and the actual classes are represented as rows. Let's calculate the number of true positives, true negatives, false positives, and false negatives from the evaluation data of a classification algorithm. Then we will construct a confusion matrix. We've given you 2 ordered lists. Actual represents the true labels of the data set. Each one in the list represents an email that is spam, and each 0 represents an email that is not spam. Predicted represents the classifications that the machine learning algorithm returned. For each email, the classifier predicted whether the email was spam or not spam. Create 4 variables to store the results. They should be called true positives, loop through each of the predictions in the list and add 1 to true positives every time the algorithm found a true positive. So I guess if actual I is equal to 1 and actual I is equal to predicted I, positives equals 1. Inside the for loop, count the number of true negatives, false positives, and false negatives. Oh, no, I don't need that. We have already imported a function confusion matrix from SciKit-Learn. Create a variable conf matrix. And pass the list of actual and predicted values to the confusion matrix function. Print conf matrix. Nice. Accuracy. One method for determining the effectiveness of a classification algorithm is by measuring its accuracy statistic. Accuracy is calculated by finding the total number of correctly classified predictions, true positives and true negatives, and dividing by the total number of predictions. Accuracy is defined as accuracy equals true positives plus true negatives over true positives plus true negatives plus false positives plus false negatives. Let's calculate the accuracy of the classification algorithm. Calculate the accuracy and store it in a variable named accuracy. Print accuracy. So accuracy equals true positives plus true negatives divided by true positives plus true negatives plus false positives plus false negatives. Oh, I forgot to print it. 0.3. Recall. Accuracy can be a misleading statistic depending on our data and the problem we are trying to solve. Consider a model task with predicting spam in the email inboxes of top secret government employees who never use their work email addresses for online shopping or logging onto their favorite gaming apps. We can write a pretty simple and accurate classifier that always predicts false. The email is not spam. This classifier will be incredibly accurate since there are hardly ever any spam emails sent to those top secret emails, but this classifier will never be able to find the information we are actually interested in when there is spam. In this situation, a helpful statistic to consider is recall. In our example, recall measures the ratio of correct spam predictions that our classifier found to the total number of spam emails. Recall is defined as recall equals true positives over true positives plus false negatives equals TP over TP plus FN. Recall is the ratio of correct positive predictions classifications made by the model to all actual positives. For the spam classifier, this would be the number of correctly labeled spam emails divided by all the emails that were actually spam in the dataset. Our algorithm that always predicts not spam might have a very high accuracy, but it never will find any true positives, so its recall will be 0. Calculate the recall and store it in a variable named recall and print recall. Positive. Precision. Unfortunately, recall isn't a perfect statistic either. Spoiler alert, there is no perfect statistic. For example, we could create a spam email classifier that always returns true. The email is spam. This particular classifier would have a low accuracy, but the recall would be 1 because it would be able to accurately find every spam email. In this situation, a helpful statistic to understand is precision. In our email spam classification example, precision is the ratio of correct spam email predictions to the total number of spam predictions. Precision is defined as precision equals true positives over true positives plus false positives equals TP over TP plus FP. Precision is the ratio of correct positive classifications to all positive classifications made by the model. For the spam classifier, this would be the number of correctly labeled spam emails divided by all the emails that were correctly or incorrectly labeled spam. The algorithm that predicts every email is spam will have a recall of 1, but it will have very low precision. It correctly predicts every spam email, but there are tons of false positives as well. Calculate the precision and store it in a variable named precision. Print the precision. That's fine. Well, I'll print it. Might as well. F1 score. It is often useful to consider both the precision and recall when attempting to describe the effectiveness of a model. The F1 score combines both precision and recall into a single statistic by determining their harmonic mean. The harmonic mean is a method of averaging. F1 score is defined as F1 score equals 2 times precision times recall over precision plus recall. We use the harmonic mean rather than the traditional arithmetic mean because we want the F1 score to have a low value when either precision or recall is 0. For example, consider a classifier where recall equals 1 and precision equals 0.02. Despite our classifier having an extremely high recall score, there is most likely a problem with this model since the precision is so low. Ideally, the F1 score would reflect that. And again, the F1 score combines both precision and recall into a single statistic by determining their harmonic mean, which is a method of averaging. So, for example, consider a classifier where recall equals 1 and precision equals 0.02. Despite our classifier having an extremely high recall score, there's most likely a problem with this model since the precision is so low. Ideally, the F1 score would reflect that. If we took the arithmetic mean of precision and recall, we get 1 plus 0.02 over 2 equals 0.51. That performance statistic is misleadingly high for a classifier that has such dismal precision. If we instead calculate the harmonic mean, we get 2 times 1 times 0.02 over 1 plus 0.02 equals 0.039. That is a much better descriptor of the classifier's effectiveness. Let's calculate the F1 score of the classification algorithm. So F1 equals 2 times, they're gonna make me do this. Okay, it's okay. So it means we have to recalculate the precision and the recall, and I like how it just expects me to have memorized those. So I'm gonna need some hints. Well, I know it's precision and recall, but I don't have those here. Well, okay. Let's see if it flags me for not having these defined. Yeah, I know. So can you remind me, please, what they were? I'll write them again just so I can remember them, but so you're definitely going to test me on this, but whatever. So precision equals true positives divided by true positives plus false positives. So essentially, precision is the true positives over the true total, and recall is the true positives over the what would you call that? True positives plus false negatives. Yeah, I don't have a good semantic to remember that. It's fine. I misspelled something, but it's fine. Review. There is no perfect metric. The decision to use accuracy, precision, recall, F1 score, or another metric not covered in this lesson ultimately comes down to the specific context of the classification problem. Take the email spam problem. We probably want a model that is high precision and do not mind as much if it has a low recall score. This is because we want to make sure the algorithm does not incorrectly send an important email message to the spam folder, while it is not as detrimental to have a few spam emails end up in our inbox. As long as you have an understanding of what question you're trying to answer, you should be able to determine which statistic is most relevant to you. The Python library SciKit-Learn has some functions that will calculate these statistics for you. You have now learned many different ways to analyze the predictive power of your classification algorithm. Here are some of the key takeaways. Classifying a single point can result in a true positive, actual equals 1, predicted equals 1, a true negative, actual equals 0, predicted equals 0, a false positive or false negative. These values are often summarized in a confusion matrix. Accuracy measures how many classifications your algorithm got correct out of every classification it made. Recall is the ratio of correct positive predictions, classifications made by the model, to all actual positives. Precision is the ratio of correct positive classifications to all positive classifications made by the model. F1 score is a combination of precision and recall. F1 score will be low if either precision or recall is low. Python's Scikit-Learn library has functions that will help you calculate accuracy, recall, precision, and F1 score. They all take two parameters, a list of the actual labels and a list of the predicted classifications. Call accuracy score using the correct parameters and print the result. Cool. Given the following values, what is the recall of the classifier? So recall is true positive over true positive plus false negative. So 2 over 2 plus 4, so 2 over 6 is 1 over 3. If the true labels of your data are 1, 0, 1, 1, and the prediction from the classifier are 1, 1, 1, 0, then the prediction at index 3 is a true positive, or 0, 1, 2, 3, sorry. If the true labels, so in the classifier, so we got a false negative. Precision is defined as the harmonic mean of accuracy and recall, the number of relevant items out of all items selected, the number of correct classifications out of all classifications. I think isn't F1 score is the harmonic mean. The precision is the true positive and true negative over everything. The number of correct classifications out of all, number of relevant items out of all items selected. So true positives, and what does that mean exactly? So accuracy is the number of correct classifications out of all classifications. Precision is true positives divided by true positives plus false positives. So the number of relevant items, which are true positives, out of all items selected. So precision is true positives divided by true positives plus false positives. In the image below, the circle with the solid line represents the true label of points. Points that fall in the circle have label 1, and points outside the circle have label 0. True label of all points. Points that fall inside the circle have label 1, and points outside the circle have label 0. The circle with the dotted line represents the classifier's guess. If the point is inside the dotted circle, it has been classified as a 1. Otherwise, it was classified as a 0. What is the equation for accuracy? So, true positives and true negatives. So, A is fall inside the circle. True label. So A is all the true positives and true negatives. Points that fall in the circle have label 1. Points outside the circle have label 0. Circle with the dotted line represents the classification's guess. If the point is inside the dotted circle, it has been classified as 1. Otherwise, it is classified as a 0. What is the equation for accuracy? AB. B plus D. True positives, true negatives over everything. Yeah. Why is the F1 score calculated using the harmonic mean? The harmonic mean makes the F1 score low when either precision or recall is low. The harmonic mean will consider precision and recall equally. The harmonic mean takes a false positive is when the true label is 0 and the prediction is 0. No. False positive is when the true label is 0 and the prediction is 1. What are the parameters of SciKit-Learn's F1 score function? A true label followed by a prediction. So, actual prediction. A list of true labels followed by a list of predictions. Correct, even if there's only one data point, one prediction needs to be in a list. At the image below, the circle with the solid line represents the true label of all points. Points that fall in the circle have the label 1. Points outside the circle have the label 0. Circle with the dotted line represents the classification's guess. If the point is in the dotted circle, it's been classified as a 1. Otherwise, it's classified as 0. Recall is true positives over true positives plus false negatives. So true positives over true positives plus false negatives. So A over A plus C. No, can't be right. Recall is true positives. I thought it was... So true positives is A. So it's either true positives over true positives plus predicted positives, which I thought was precision, or it's true positives over true positives plus false negatives. Damn it. What it is actually predicted. So D represents true negatives and A represents false negatives. Oh. is true positives. I understand now. True positives over true positives plus false negatives. I'm confused by that, but it's fine. It's whatever. I don't think I need to have those necessarily memorized. I'll get better at it as time goes on. How am I doing with time? Doing good. I'm just getting lazy. I need to not be lazy. Okay? Don't be lazy. Still have a significant amount of time to go. So keep going. Okay, keep going. Let me just change something real quick. Okay, support vector machines. A support vector machine, SVM, is a powerful supervised machine learning model used for classification. An SVM makes classifications by defining a decision boundary and then seeing what side of the boundary an unclassified point falls on. In the next few exercises, we'll learn how these decision boundaries get defined, but for now, an SVM makes classifications by defining a decision boundary and then seeing what side of the boundary an unclassified point falls on. In the next few exercises, we'll learn how these decision boundaries get defined, but for now, know that they're defined by using a training set of classified points. That's why SVMs are supervised machine learning models. Decision boundaries are easiest to wrap your head around when the data has two features. In this case, the decision boundary is a line. Take a look at the example below. A decision boundary in 2 dimensions. We have our average number of goals and the average time to catch snitch. So playoff teams get a high number of goals in a low amount of time, and non-playoff teams get a low number of goals in a high number of time. Note that if the labels on the figures in this lesson are too small to read, you can resize this pane to increase the size of the images. Okay. This SVM is using data about fictional games of Quidditch from the Harry Potter universe. The classifier is trying to predict whether a team will make the playoffs or not. Every point in the training set represents a historical Quidditch team. Each point has 2 features: the average number of goals the team scores and the average number of minutes it takes the team to catch the golden snitch. After finding a decision boundary using the training set, you could give the support vector machine an unlabeled data point and will predict whether or not that team will make the playoffs. Decision boundaries exist even when your data has more than 2 features. If there are 3 features, the decision boundary is now a plane rather than a line. As the number of dimensions grows past 3, it becomes very difficult to visualize these points in space. Nonetheless, support vector machines can still find a decision boundary. However, rather than being a separating line or a separating plane, the decision boundary is called a separating hyperplane. Run the code to see 2 graphs appear. Right now they should be identical. We're going to fix the bottom graph so it has a good decision boundary. Why is this decision boundary bad? Because it's not indicative of the difference. Let's shift the line on the bottom graph to make it separate the 2 clusters. The slope of the line looks pretty good, so let's keep that at -2. We want to move the boundary up, so change intercept 2. So the line separates the 2 clusters. So right now its intercept is 8. We could make its intercept, I don't know, let's say 20. It's not that great. Let's make it 16. It's pretty good. Optimal decision boundaries. One problem that support vector machines need to solve is figuring out what decision boundary to use. After all, there could be an infinite number of decision boundaries that correctly separate the 2 classes. Take a look at the image below. Different decision boundaries: graph A, graph B, graph C, graph D, graph E, graph F. There are so many valid decision boundaries, but which one is best? In general, we want our decision boundary to be as far away from training points as possible. Maximizing the distance between the decision boundary and points in each class will decrease the chance of false classification. Take graph C, for example. The decision boundary is close to the blue class, so it is possible that a new point close to the blue cluster would fall on the red side of the line. Out of all the graphs shown here, graph F has the best decision boundary. Run the code. Both graphs have suboptimal decision boundaries. Why? We're going to fix the bottom graph. It needs a better slope. We're going to have to make the decision boundary much flatter, which means we first need to follow its y-intercept. Change intercept 2 to be 8. Okay. Next, we want the slope to be pretty flat. Change the value of slope 2. The resulting line should split the two clusters. So let's try slope of 2. Negative 2, I mean. No, not good enough. Should be greater than negative 2. That looks good to me. Support vector margins. Support vectors and margins. We now know that we want our decision boundary to be as far away from our training points as possible. Let's introduce some new terms that can help explain this idea. Support vectors are the points in the training set closest to the decision boundaries. Again, the support vectors are the points in the training set closest to the decision boundaries, to the decision boundary. In fact, these vectors are what define the decision boundary. But why are they called vectors? Instead of thinking about the training data as points, we can think of them as vectors coming from the origin. These vectors are crucial in defining the decision boundary. That's where the support comes from. If you are using n features, there are at least n plus 1 support vectors. The distance between a support vector and the decision boundary is called the margin. We want to make the margin as large as possible. The support vectors are highlighted in the image below. Because the support vectors are so critical in defining the decision boundary, many of the other training points can be ignored. This is one of the advantages of support vector machines. Many supervised machine learning algorithms use every training point in order to make a prediction. Even though many of those training points aren't relevant, support vector machines are fast because they only use the support vectors. What are the support vectors for the SVM picture below? There should be 2 blue support vectors and 1 red support vector. Finish defining red support vector, blue support vector 1, and blue support vector 2. Set them equal to the correct points. The point should be represented as a list like so. So red is 1.06, or okay. So I guess we're doing y-axis first. I know, but this is misleading. Let's be real, that is misleading. But regardless. Oh, I got it backwards. Right, so 1.06, 0.52, and 2.52. What is the size of the margin? Find the total distance between a support vector and the line by looking at the graph. Two. SciKit-Learn. Now that we know the concepts behind support vector machines, we need to write the code that will find the decision boundary that maximizes the margin. All of the code that we've written so far has been guessing and checking. We don't actually know if we found the best line. Unfortunately, calculating the parameters of the best decision boundary is a fairly complex optimization problem. Luckily, Python's SciKit-Learn library has implemented an SVM that will do this for us. Note that while it is not important to understand how the optimal parameters are found, you should have a strong conceptual understanding of what the model is optimizing. To use SciKit-Learn's support vector machine, we first need to create an SVC object. It is called an SVC because Scikit-Learn is calling the model a support vector classifier rather than a support vector machine. Classifier equals SVC kernel equals linear. We'll soon go into what the kernel parameter is doing, but for now let's use a linear kernel. Next, the model needs to be trained on a list of data points and a list of labels associated with those data points. The labels are analogous to the color of the point. You can think of a 1 as a red point and a 0 as a blue point. The training is done using the .fit method. So training points equals a list of lists 1, 2, 1, 5, 2, 2, and so on. The labels are 1, 1, 1, 0, 0, 0. Classifier.fit training points to the labels. The graph of this data set would look like this. Calling .fit creates the line between the points. Finally, the classifier predicts the label of new points using the .predict method. The .predict method takes a list of points you want to classify. Even if you only want to classify one point, make sure it is in a list. So print classifier.predict 3, 2. In the image below, you can see the unclassified point 3, 2 as a black dot. So right there, it falls on the red side of the line, so the SVM we predicted is red. In addition to using the SVM to make predictions, you can inspect some of its attributes. For example, if you can print classifier.support vectors to see which points from the training set are the support vectors. In this case, the support vectors look like this: 7, 5, 8, 2, 2, 2. Let's start by making a SVC object with kernel equals linear. Name the object classifier. We've imported the training set and labels for you. Call classifiers.fit method using points and labels as parameters. We can now classify new points. Try classifying both of those. Remember, the .predict function expects a list of points to predict. So print classifier.predict 3, 4. 6, 7, 0, and 1. Outliers. Support vector machines try to maximize the size of the margin while still correctly separating the points of each class. As a result, outliers can be a problem. Consider the image below. So an SVMs with a high value for C, a hard margin. SVMs with a low value for C, a soft margin. The size of the margin decreases when a single outlier is present, and as a result, the decision boundary changes as well. However, if we allow the decision boundary to have some error, we could still use the original line. So again, SVMs try to maximize the size of the margin while still correctly separating the points of each class. As a result, outliers can be a problem. Consider the image below. An SVMs with a high value for C, a hard margin. So here the blues are on the right side and the reds are on the right side. If we had an SVM with a low value for C, a soft margin, then we'd have this blue on the red side and this red on the blue side. The size of the margin decreases when a single outlier is present, and as a result, the decision boundary changes as well. However, if we allow the decision boundary to have some error, we could still use the original line. SVMs have a parameter C that determines how much error the SVM will allow for. If C is large, then the SVM has a hard margin. It won't allow for many misclassifications, and as a result, the margin could be fairly small. If C is too large, the model runs the risk of overfitting. It relies too heavily on the training data, including the outliers. On the other hand, if C is small, the SVM has a soft margin. Some points might fall on the wrong side of the line, but the margin will be large. This is resistant to outliers, but if C gets too small, you run the risk of underfitting. The SVM will allow for so much error that the training data won't be represented. When using SciKit-Learn's SVM, you can set the value of C when you create the object. Classifier equals SVC, C equals 0.01. The optimal value of C will depend on your data. Don't always maximize margin size at the expense of error. Don't always minimize error at the expense of margin size. The best strategy is to validate your model by testing many different values for C. Run the code to see the SVM's current boundary line. Note that we've imported some helper functions we wrote named draw points and draw margins to help visualize the SVM. Let's add an outlier. Before calling .fit, append 3.3 to points. So and append 0 to labels. Right now our classifier has hard margins because C equals 1. Change the value of C to 0.01. See what the SVM looks like with soft margins. Oh. Append at least 2 more points to points. If you want the points to appear on the graph, make sure their X and Y values are between 0 and 12. Make sure to also append a label to labels for every point you add. A 0 make the point blue and a 1 will make the point red. Make sure to add the points for training the SVM. How do I do this? I guess I gotta do them separately, huh? Sure that there's a better way, but whatever. Play around with the C variable to see how the decision boundary changes with your new points added. Kernels. Up to this point, we have been using data sets that are linearly separable. This means that it's possible to draw a straight decision boundary between the two classes. However, what would happen if an SVM came along a data set that wasn't linearly separable? So non-linearly separable data, it's like so. It's impossible to draw a straight line to separate the red points from the blue points. Luckily, support vector machines have a way of handling these data sets. Remember when we set kernel equals linear when creating our SVM? Kernels are the key to creating a decision boundary between data points that are not linearly separable. Note that most machine learning models should allow for some error. For example, the image below shows data that isn't linearly separable. However, it is not linearly separable due to a few outliers. We can still draw a straight line that, for the most part, separates the two classes. You shouldn't need to create a non-linear decision boundary just to fit some outliers. Drawing a line that correctly separates every point will be drastically overfitting the model to the data. Let's take a look at the power of kernels. We've created a data set that isn't linearly separable and split it into a training set and a validation set. Create an SVC named classifier with a linear kernel. Call the .fit method. Using training data. Training labels. Its parameters. Let's see how accurate our classifier is using a linear kernel. call classifiers dot score function using validation data and validation labels as parameters. Print the results. So print the average accuracy of the model. That's pretty bad. The classifier is getting it right less than 50% of the time. Change linear to poly. And add the parameter degree equals 2. Run the program again and see what happens to the score. It's getting it right every time. It's pretty impressive. Polynomial kernel. That kernel seems pretty magical. It is able to correctly classify every point. Let's take a deeper look at what it was really doing. We start with a group of non-linearly separable points that look like this. The kernel transforms the data in a clever way to make it linearly separable. We used a polynomial kernel which transforms every point in the following way. X, y goes to the square root of 2 times x times y, x squared and y squared. The kernel has added a new dimension to each point. For example, the kernel transforms the point 1, 2 like this. So 1, 2 becomes 2 square roots of 2, 1, and 4. So that would be, so 2 square root of 2 is just over 1. 2 of that would be over here. 1, I'm confused. Okay. If we plot these new 3-dimensional points, oh, I see. Get the following graph. Look at that. All of the blue points have scooted away from the red ones. By projecting the data into a higher dimension, the two classes are now linearly separable by a plane. We could visualize what this plane would look like in 2 dimensions to get the following decision boundary. In this exercise, we will be using a non-linearly separable data set similar to the concentric circles above. Rather than using a polynomial kernel, we're going to stick with a linear kernel and do the transformation ourselves. The support vector machine running a linear kernel on the transform points should perform identically to the SVM running a polynomial kernel on the original points. To begin, at the bottom of your code, print training data 0 to see the first data point. Let's transform the data into 3 dimensions. Begin by creating 2 empty lists called new training and new validation. Loop through every point in training data. For every point, append a list to new training. So for the list should contain 3 numbers. The square root of 2 times 0.0. So we'll say for I in range length of training data, point equals training data I. So when we printed training data 0, this is what it looks like, right? So say that's it. Point equals so training data 0 is a point itself. So if we say for the first iteration, this would be what point is. So loop through every point in training data. For every point, append a list to new training. The list should contain 3 numbers. So the square root of 2 times, so square root of 2 number, square number, in Python do number. 2, take the square root. So 2 times this to 0.5 power times 0.0 times 0.1, 0.0 to the second power, 0.1 to the second power. Invalid syntax. Oh, I see. Do the same for every point in validation data. For every point in validation data, add the new list to new validation. Retrain classifier by calling the .fit method. Using new training. Training labels as parameters. Finally, run classifier's score method. We're gonna want to print this, huh? Yeah, print classifier dot score new validation labels. Print the results. Did perfectly. Radial basis function kernel. The most commonly used kernel in support vector machines is a radial basis function RBF kernel. This is the default kernel used in SciKit-Learn's SVC object. If you don't specifically set the kernel to linear poly, the SVC object will use an RBF or radial basis function kernel. If you want to be explicit, you can set kernel equals RBF, although that is redundant. It is very tricky to visualize how an RBF kernel transforms the data. The polynomial kernel we use transformed 2-dimensional points into 3-dimensional points. An RBF kernel transforms 2-dimensional points into points with an infinite number of dimensions. We won't get into how the kernel does this. It involves some fairly complicated linear algebra. However, it is important to know about the RBF kernel's gamma parameter. Classifier equals SVC, so support vector classifier. Kernel equals RBF, gamma equals 0.5, C equals 2. Gamma is similar to the C parameter. You can essentially tune the model to be more or less sensitive to the training data. A higher gamma, say 100, will put more importance on the training data and could result in overfitting. Conversely, a lower gamma, like 0.01, makes the points in the training data less relevant and can result in underfitting. We're going to be using a RBF kernel to draw a decision boundary for the following points. We've imported the data for you and split it into training data, validation data, training labels, and validation labels. Begin by creating an SVC named classifier with an RBF kernel. Set the kernel's gamma equal to 1. SVC, oh. Next, train the model using .fit. Method using training data, training labels, parameters. Let's test the classifier's accuracy when its gamma is 1. Print classifier dot score. Function using validation data. Validation labels. Goodness. Let's see what happens if we increase gamma. So we got about 88.88%. Change the gamma to 10. Happens to the accuracy of our model. Goes down. The accuracy went down. We overfit our model. Change gamma to 0.1. What happens to the accuracy of our model? This time it goes down even further. Review. Great work. Here are some of the major takeaways from this lesson on support vector machines. Support vector machines are supervised machine learning models used for classification. An SVM uses support vectors to define a decision boundary. Classifications are made by comparing unlabeled points to that decision boundary. Support vectors are the points of each class closest to the decision boundary. The distance between the support vectors and the decision boundary is called the margin. Support vector machines attempt to create the largest margin possible while staying within an acceptable amount of error. The C parameter controls how much error is allowed. A large C allows for little error and creates a hard margin. A small c allows for more error and creates a soft margin. Support vector machines use kernels to classify points that aren't linearly separable. Kernels transform points into higher dimensional space. A polynomial kernel transforms points into 3 dimensions, while an RBF kernel transforms points into infinite dimensions. An RBF kernel has a gamma parameter. If gamma is large, the training data is more relevant, and as a result, overfitting can occur. What happens to a support vector machine if C is too large? Underfitting will occur due to the margin becoming too large. Overfitting will occur due to the margin becoming too small. Overfitting will occur due to the margin becoming too large. Underfitting will occur due to the margin becoming too small. So I'm getting exposed right now for not fully paying attention to even just that last thing I was reading. So focus. I believe C represents the hardness of the margin. So a soft margin means a low C. No. I think a soft margin means a large C. So a small c, if a c is too large, we get a soft margin, which means it will underfit, occur due to the margin becoming too large. Damn it. Overfitting, I had it completely backwards. So a small c means the margin becomes large and will underfit. A large c means the margin becomes small and will overfit. Okay. An SVM has a soft margin when the support vectors are the points farthest away from the decision boundary. The support vectors are the closest points from one class, not both. The margin is small, and the decision boundary allows few errors. Margin is large, and the decision boundary allows for many errors. If your data is in 3 dimensions, the decision boundary will be a plane. Correct, a plane can separate points in 3 dimensions. Which of the following support vector machines has an optimal decision boundary? This looks very good. This looks worse. This looks worse. This looks worse. Let's say A. What are the support vectors in an SVM? Points in the training set that fall directly on the decision boundary. All points in closest decision boundary. What is the role of a kernel in an SVM? A kernel chooses which data points should be in the training set. No. Sets the margins of an SVM to be there. Kernel transforms the data into higher dimensions from linear separable. Boom. Kernels help make decision boundaries for points that are not linearly separable. What are the inputs of the .fit method in SciKit-Learn's SVC class? They are a list of training points and a list of labels associated with those points. Correct. These both have to be lists, even if you're only training with one data point, which you probably shouldn't do. Which of the following SVMs with an RBF kernel has the largest gamma parameter? So gamma is similar to C. So a large C means we have very small margins. So a large gamma would mean probably look like C. Correct. The highest gamma will be the graph that is most overfit to the data. The decision boundary will be very specific to the training set. Why is it important for an SVM to maximize the size of its margin? A large margin. Why is it important to maximize a large margin? Prevents points in the training set from being too close to the decision boundary. Small margin will result in underfitting. Size of the margin doesn't matter as long as the data is linearly separable. A large margin makes more of the training points relevant. um, so I guess, is it true that a small margin will result in underfitting? No. Is it true that a large margin makes more of the training points relevant? Yes. Damn it. A large margin prevents points in the training set from being close to the decision boundary. I see. Getting iteratively worse at this. So, what's next? Naive Bayes classifier. Let's get it. Introduction to Bayes' theorem. In this lesson, we'll learn about Bayes' theorem. Bayes' theorem is the basis of a branch of statistics called Bayesian statistics, where we take prior knowledge into account before calculating new probabilities. This allows us to find narrow solutions from a huge universe of possibilities. British mathematician Alan Turing used it to crack the German Enigma code during World War II, and now it is used in machine learning, statistical modeling, A/B testing, robotics. By the end of this lesson, you'll be able to solve simple problems involving prior knowledge. Before we learn this theorem, we'll need to review independence and conditional probability. Independent events. The ability to determine whether two events are independent is an important skill for statistics. If two events are independent, then the occurrence of one event does not affect the probability of the other event. Here are some examples of independent events. I wear a blue shirt. My coworker wears a blue shirt. I take the subway to work. I eat sushi for lunch. The New York Giants win their football game. The New York Rangers win their hockey game. If two events are dependent, then when one event occurs, the probability of the other event occurring changes in a predictable way. Here are some examples of dependent events. It rains on Tuesday. I carry an umbrella to work. It rains on Tuesday. I carry an umbrella on Tuesday. I eat spaghetti. I have a red stain on my shirt. I wear sunglasses. I go to the beach. A certain family plans to have 3 children. Is the event that the couple's third child is a girl independent of the event that the couple's first 2 children are girls? Yes. Conditional probability. Conditional probability is the probability that 2 events happen. It's easiest to calculate conditional probability when the 2 events are independent. For the rest of this lesson, we'll be using the statistical convention that the probability of an event is written as P of event. If the probability of event A is P of A, then the probability of event B is P of B, and the 2 events are independent, then the probability of both events occurring is the product of the probabilities P of, so A and B equals P of A cross B of P of B, or I don't know if I should say cross or times. The symbol upside down U just means and. So P of A and B means the probability that both A and B happen. For instance, suppose we are rolling a pair of dice and want to know the probability of rolling 2 sides. Each die has 6 sides, so the probability of rolling a 6 is 1/6. Each die is independent. Rolling 1/6 does not increase or decrease our chance of rolling a second 6. So the probability of rolling 1/6 and another 6 equals the probability of 6 times probability of 6 equals 1/6 times 1/6 equals 1/36. This week there is a 30% probability that it will rain on any given day. At a certain high school, gym class is held on 3 days out of the 5-day school week. On a school day, what is the probability that it is raining and the students have gym class? Save your answer to the variable P, rain, and gym. Maybe not. So the probability of rain, 30%. So can I do 3-3? I mean, why did they choose 30%? Oh, okay, I see. So, okay, I got you. P rain is 0.30. P gym. Oh, yeah. Got you. It's not 1 and 5, it's 3 and 5. Actually, it was 5 and 7. Whatever. Testing for a rare disease. Suppose you are a doctor and you need to test if a patient has a certain rare disease. The test is very accurate. It's correct 99% of the time. The disease is very rare. Only 1 in 100,000 patients have it. You administer the test and it comes back positive, so your patient must have the disease, right? Not necessarily. If we just consider the test, there is only a 1% chance that it is wrong, but we actually have more information. We know how rare the disease is. Given that the test came back positive, there are 2 possibilities. The patient had the disease, and the test correctly diagnosed the disease. The patient didn't have the disease, and the test incorrectly diagnosed that they had the disease. What is the probability that the patient had the disease and the test correctly diagnosed the disease? Save your answer to the variable P disease and correct. So I didn't really digest that. So we're a doctor and we need to test if a patient has a certain rare disease. Test is accurate, it's correct 99% of the time. Disease is very rare, only 1 in 100,000 patients have it. So test is right. Disease rare. You administer the test and it comes back positive, so your patient must have the disease, right? Not necessarily. If we just consider the test, there's only 1% chance that it is wrong, but we actually have more information. We know how rare the disease is. Given that the test came back positive, there are 2 possibilities. The patient had the disease and the test correctly diagnosed the disease. The patient didn't have the disease and the test incorrectly diagnosed that they had the disease. What is the probability that the patient had the disease and the test correctly diagnosed the disease? Probability that the test is right times the rarity of the disease, the probability of having the disease. What is the probability that the patient does not have the disease and the test? So we'll say call this, just to make it understandable, P test right, P of disease, and so the P disease incorrect is P test right times P of disease. So now they're asking, what is the probability that the patient does not have the disease and the test incorrectly diagnosed the disease? So P no disease and incorrect. So now it's asking this probability the patient does not have the disease. So we could do 1 minus probability of disease times disease and the test incorrectly diagnosed the disease, and 1 minus P test right. Print both of them. So it's actually much more likely that they don't have the disease and the test was incorrect. It's very unlikely that they actually have the disease and the test was correct. Bayes' theorem. In the previous exercise, we determined two probabilities. The patient had the disease and the test correctly diagnosed the disease. The patient didn't have the disease and the test incorrectly diagnosed that they had the disease. Both events are rare, but we can see that it was about 1,000 times more likely that the test was incorrect than that the patient had this rare disease. We're able to come to this conclusion because we had more information than just the accuracy of the test. We also knew the prevalence of this disease. In statistics, if we have two events, A and B, we write the probability that event A will happen, given that event B already has happened, as P A pi B. In other words, we want to find P rare disease positive result. In other words, we want to find the probability that the patient has the disease given the test came back positive. So we'd say, probability of A given B. In our example, we want to find the probability of rare disease given positive result. In other words, we want to find the probability that the patient has disease given the test came back positive. We can write P of A given B using Bayes' theorem, which states the probability of A given B equals the probability of B given A times probability of A over the probability of B. So in this case, we'd say the probability of a rare disease given a positive result is equal to the probability of a positive result given the rare disease times the probability of the rare disease over the probability of the positive result. It is important to note that on the right side of the equation, we have the term probability of B given A. This is the probability that event B will happen given the event A has already happened. This is very different from probability of A given B, which is the probability we are trying to solve for. The order matters. Calculate probability of the positive result given the rare disease, or the probability of a positive test result given that a patient really has this rare disease. Save your answer as a decimal. Probability positive given disease. So in our numerator, we know we're going to want the probability of that they have the disease. So can you remind me what the probabilities are again? So probability of a positive result given the rare disease. I'm getting confused here. Okay. So P positive given disease was 0.99. Okay, that makes sense. So the numerator is P positive. Let's just make this simple on ourselves, right? 0.99 times probability of the rare disease, which was 1 over 100,000. And we're going to divide all of this by the probability of a positive result, which is probability of a positive result is 0.01. What is probability of rare disease? The probability that a randomly selected patient has the rare disease. We now need to compute the denominator. We need the positive results. Oh, I think I tried to jump too many steps ahead. That's why, oh no. We now need to compute the denominator. We need to find P positive result. As we discussed previously, there are two ways to get a positive result. The patient had the disease and the test correctly diagnosed the disease. The patient didn't have the disease and the test incorrectly diagnosed that they had the disease. Using these two probabilities, calculate the total probability that a randomly selected patient receives a positive test result, P positive result. Save your answer to the variable P positive. So, okay, so we'll say P positive 1. The patient had the disease, which is a 1 in 100,000 chance. And the test correctly diagnosed the disease. So 9 and P positive 2. The patient didn't have the disease, which is a 1 minus 1 divided by 100,000, and the test incorrectly diagnosed that they had the disease, 0.01. These are the two ways to get the positive result. Using these two probabilities, calculate the total probability that a randomly selected patient receives a positive test result. So then P positive would be both of these probabilities added up. Nice. Substitute all three of these values into Bayes' theorem and calculate P rare disease given positive result. So P disease given positive result. So probability of a positive result given disease times probability of the disease and divide this by probability of a positive result. And then print this. This is the probability that they have the disease given the positive result. It's still very low. Is it likely that your patient has this disease? No. This is about 0.1%. Spam filters. Let's explore a different example. Email spam filters use Bayes' theorem to determine if certain words indicate that an email is spam. Let's take a word that often appears in spam, enhancement. With just 3 facts, we can make some preliminary steps towards a good spam filter. 1. Enhancement appears in just 0.1% of non-spam emails. 2. Enhancement appears in 5% of spam emails. 3. Spam emails make up about 20% of total emails. Given that an email contains enhancement, what is the probability that the email is spam? In this example, we are dealing with 2 probabilities. Probability of enhancement, the probability that the word enhancement appears in an email, probability of spam, the probability that an email is spam. Using Bayes' theorem to answer our question means that we want to calculate the probability of A given B, but what are A and B referring to in this case? Save the string spam to the variable A. Enhancement. What is probability of spam? So P spam is 1. Oh no. Probably spam is 0.2. What is probability of enhancement given spam? P so if it's spam, probability of enhancement is 0.05. We want to know the overall probability that any email, spam or non-spam, contains enhancement. Because we know the probability of enhancement occurring in both spam and non-spam emails, we can use a weighted average to calculate the probability of enhancement occurring in an email. So sorry, what is happening? I hit the wrong button. That's what's happening. So P enhancement equals P enhancement given spam times P spam plus P enhancement not spam times P not spam Now that we know P spam, P enhancement given spam, and P enhancement, we can plug this into Bayes' theorem. So P spam given enhancement equals P enhancement given spam times P spam divided by P enhancement. I got it backwards, huh? No, I just misspelled it. Enhancement. We're looking for the probability that this email is spam, given it has the word enhancement. So we look at the probability of the word enhancement given spam times the probability of spam, and we divide all that by the probability of enhancement. Where am I messing up? So I didn't mess up, it's just that I didn't print it. And I think they just don't like the way that I wrote it actually. Whatever. Print P spam enhancement. This is probably that an email is spam given that it contains the word enhancement. Should we block all emails that contain enhancement? How much non-spam email will we block? I mean, it looks like we probably should do it, yeah. yeah. Probably block it if it says that. Review. In this course, we learned several new definitions. Two events are independent if the occurrence of one event does not affect the probability of the second event. If two events are independent, then probability of A and B equals probability of A times probability of B. Bayes' theorem is the following: probability of A given B equals probability of B given A times probability of A over probability of B. Why do we choose the Bayesian approach over the frequentist approach? What are the differences? So, what should I do? This is the syllabus. What should I do? Definitely keep going. I might have to stop this halfway through. The naive Bayes classifier. A naive Bayes classifier is a supervised machine learning algorithm that leverages Bayes' theorem to make predictions and classifications. Recall Bayes' theorem: probability of A given B equals probability of B given A times probability of A over probability of B. This equation is finding the probability of A given B. This can be turned into a classifier if we replace B with a data point and A with a class. For example, let's say we're trying to classify an email as either spam or not spam. We could calculate probability of spam given an email and probability of not spam given an email. Whichever probability is higher will be the classifier's prediction. Naive Bayes classifiers are often used for text classification. So why is this a supervised machine learning algorithm? In order to compute the probabilities used in Bayes' theorem, we need previous data points. For example, in the spam example, we'll need to compute probability of spam. This can be found by looking at a tagged dataset of emails and finding the ratio of spam to non-spam emails. Here are some helpful links to the top questions asked by coders about this exercise. With a naive Bayes classifier, we are finding the probability that data point D is a member of a class C using Bayes' theorem. We can determine probability of C. Because this model is supervised, we have data. But what is probability of D? How do we find the probability of a data point? Investigate the data. In this lesson, we are going to create a naive Bayes classifier that can predict whether a review for a product is positive or negative. This type of classifier could be extremely helpful for a company that is curious about the public reaction to a new product. Rather than reading thousands of reviews or tweets about the product, you could feed those documents into the naive Bayes classifier and instantly find out how many are positive and how many are negative. The dataset we will be using for this lesson contains Amazon product reviews for baby products. The original dataset contained many different features, including the reviewer's name, the date the review was made, and the overall score. We've removed many of those features. The only features that we're interested in are the text of the review and whether the review is positive or negative. We labeled all reviews with a score less than 4 as a negative review. Note that in the next 2 lessons, we've only imported a small percentage of the data to help the code run faster. We'll import the full dataset later when we put everything together. Let's look at the data given to us. So print pause list 0. You classify this review as positive or negative. Perfect for new parents. We were able to, so definitely positive. Take a look at the first review in the neg list. Wanted to love this, but it's pretty expensive. So yeah, it looks negative. We've also created a counter object for all of the positive reviews and one for all of the negative reviews. These counters are like Python dictionaries. You can find the number of times the word baby was used in the positive reviews by printing pause counter baby. Print the number of times the word crib was used, so pause counter crib. Oh, in both. Bayes' theorem 1. For the rest of this lesson, we're going to write a classifier that can predict whether the review, "This crib was amazing," is a positive or negative review. We want to compute both probability of positive given review and probability of negative given review and find which probability is larger. To do this, we'll be using Bayes' theorem. Let's look at Bayes' theorem for probability of positive given review. Probability of positive given review equals probability of review given positive times the probability of positive over the probability of review. The first part of Bayes' theorem that we are going to tackle is probability of positive. This is the probability that any review is positive. To find this, we need to look at all of our reviews in our data set, both positive and negative, and find the percentage of reviews that are positive. We've bolded the part of Bayes' theorem we're working on. Find the total number of positive reviews by finding the length of pos list. Do the same for neg list. Add those two numbers together and save the sum in a variable called total reviews. Create variables named %pos and %neg. %pos should be the number of positive reviews divided by total reviews. Goodness. Print %neg and %pos. Print. Bayes' theorem 2. Let's continue to try to classify the review. This crib was amazing. The second part of Bayes' theorem is a bit more extensive. We now want to compute probability review given positive. In other words, if we assume that the review is positive, then the probability that the words "this crib was amazing" are the only words in the review. What is the probability that the words "this crib was amazing" are the only words in the review? To find this, we have to assume that each word is conditionally independent. This means that one word appearing doesn't affect the probability of another word from showing up. This is a pretty big assumption. We now have this equation. You can scroll to the right to see the full equation. So probability this crib was amazing given positive review equals probability of this given a positive, probability of crib given a positive, and so on. Let's break this down even further by looking at one of these terms. Probability of a crib given a positive review is the probability that the word crib appears in a positive review. To find this, we need to count up the total number of the times crib appeared in our data set of positive reviews. If we take that number and divide it by the total number of words in our positive review data set, we will end up with the probability of crib appearing in a positive review. If we do this for every word in our review and multiply the results together, we will have probability of review given positive, of this specific review given positive. Let's first find the total number of words in all positive reviews. Store that number in a variable named total pos. To do this, we can use the built-in Python sum function. Sum takes a list as a parameter. The list that you want to sum is the values of the dictionary pos counter. Create two variables named pos probability. Each should start at 1. These are the variables we're going to use to keep track of the probabilities. Create a list of the words in review and store it in a variable named review words. Do this using Python split function. Loop through every word in review words. Find the number of times a word appears in the pos counter and neg counter. Store these values in variables named word in pos and word in neg. for word and review words. For word in because all the words are discrete, it doesn't really matter. Inside the for loop, set the pause probability to be pause probability multiplied by word and pause divided by total pause. So probability of crib given positive equals number of crib in positive, so word in pause, divided by number of words in positive. That's the probability of crib given positive, or multiplying probability of crib given positive by the positive probability in general. Do the same multiplication for neg probability. So much higher probability that it's negative, or sorry, that it's positive, even though they're both very low in general. Smoothing. In the last exercise, one of the probabilities that we computed was the following: probability of crib given positive equals the number of crib in positive, number of words in positive. But what if crib was never in any of the positive reviews in our data set? This fraction would then be 0, and since everything is multiplied together, the entire probability of review given positive would become 0. This is especially problematic if there are typos in the review we are trying to classify. If the unclassified review has a typo in it, it is very unlikely that the same exact typo will be in the data set and the entire probability will be 0. To solve this problem, we will use a technique called smoothing. In this case, we smooth by adding 1 to the numerator of each probability and n to the denominator of each probability. N is the number of unique words in our review data set. For example, probability of crib given positive goes from this. Probability of crib given positive equals number of crib in positive over number of words in positive to this. Probability of crib given positive equals number of crib in positive plus 1 over number of words in positive plus n. Let's demonstrate how these probabilities break if there's a word that never appears in the given data sets. Change review to this crib with 2 B's was amazing. Notice the second B in crib. Inside your for loop, when you multiply pause probability and neg probability by a fraction, add 1 to the numerator. Oh yeah. In the denominator of those fractions, add the number of unique words in the appropriate data set for the positive probability. This should be the length of pos counter, which can be found by using len. And similarly for here. Did smoothing fix the problem? Yes, it did. Classify. If we look back to Bayes' theorem, we've now completed both parts of the numerator. We now need to multiply them together. So probability positive given review equals probability of review given positive times probability of positive. Let's now consider the denominator, probability of review. In our small example, this is the probability that this crib was and amazing are the only words in the review. Notice that this is extremely similar to probability of review given positive. The only difference is that we don't assume that the review is positive. However, before we start to compute the denominator, let's think about what our ultimate question is. We want to predict whether the review, this crib was amazing, is a positive or negative review. In other words, we're asking whether probability of positive given the review is greater than probability of negative given the review. If we expand those two probabilities, we end up with the following equations. Probability of positive given review equals probability of review given positive times probability of positive over probability of review, and probability negative given review equals probability of review given negative times probability of negative over probability of review. Notice that probability of review is in the denominator of each. That value will be the same in both cases. Since we're only interested in comparing these two probabilities, there's no reason why we need to divide them by the same value. We can completely ignore the denominator. Let's see if our review is more likely to be positive or negative. After the for loop, multiply pos probability by percent pos and neg probability by percent neg. Store them in final pos and final neg. Compare final pos to final neg. Final pos is greater than final neg. Print the review is positive, else the review is negative. Looks like it got it pretty good. Place the review. This crib was amazing. Wait, did our naive Bayes class get it right for this crib was amazing? Place review with one that you think should be classified as negative. It's awful. It's working right. Why are you coming at my neck? Oh, because I misspelled negative. Formatting the data for SciKit-Learn. Congratulations, you've made your own naive Bayes text classifier. If you have a data set of text that has been tagged with different classes, you can give your classifier a brand new document and it will predict what class it belongs to. We are now going to look at how Python's SciKit-Learn library can do all of that work for us. In order to use Scikit-Learn's naive Bayes classifier, we need to first transform our data into a format that Scikit-Learn can use. To do so, we're going to use Scikit-Learn's count vectorizer object. To begin, we need to create a count vectorizer and teach it the vocabulary of the training set. This is done by calling the .fit method. For example, in the code below, we've created a count vectorizer that has been trained on the vocabulary training, review, one, and second. Vectorizer equals count vectorizer, vectorizer.fit, training review 1, second review. After fitting the vectorizer, we can now call its transform method. The transform method takes a list of strings and will transform those strings into counts of the trained words. Take a look at the count below, at the code below. Counts equals vectorizer dot transform. The one review, two review. Counts counts now stores the array 2, 1, 0, 0. The word review appeared twice. The word 1 appeared once, and neither training nor second appeared at all. But how do we know that the 2 corresponds to review? You can print vectorizer.vocabulary to see the index that each word corresponds to. It might look something like this: 1, 1, training 2, review 0, second 3. Finally, notice that even though the word 2 was in our new review, there wasn't an index for it in the vocabulary. This is because 2 wasn't in any of the strings used in the .fit method. We can now use counts as input to our naive base classifier. Note that in the code in the editor, we've imported only a small percentage of our review dataset to make load times faster. We'll import the full dataset later when we put all the pieces together. Create a count vectorizer and name it counter. Call counters.fit method. .fit takes a list of strings and it will learn the vocabulary of those strings. We want our counter to learn the vocabulary from both neglist and pause list. Call .fit using neglist plus pause list as a parameter. Print counter.vocabulary. This is the vocabulary that your counter just learned. The numbers associated with each word are the indices of each word when you transform a review. Let's transform our brand new review. Create a variable named review counts and set it equal to the counters.transform function. Remember, .transform takes a list of strings to transform, so call .transform using review. As a parameter, print review counts to array. If you don't include the to array, review counts won't print in a readable format. It looks like this is an array of all zeros, but the indices that correspond to the words "this crib was amazing" should all be 1. Oh yeah, okay. We'll use review counts as the test point for the naive base classifier, but we also need to transform our training set. Our training set is neglist plus pause list. Call .transform using that parameter. Store the results in a variable named training counts. Using SciKit-Learn. Now that we've formatted our data correctly, we can use it using SciKit-Learn. SciKit-Learn's multinomial NB classifier. This classifier can be trained using the .fit method. .fit takes 2 parameters, the array of data points, which we just made, and an array of labels corresponding to each data point. Finally, once the model has been trained, we can use the .predict method to predict the labels of new points. .predict takes a list of points that you want to classify, and it returns the predicted labels of those points. Finally, .predict proba will return the probability of each label given a point. Instead of just returning whether the review was good or bad, it will return the likelihood of a good or bad review. Note that in the code editor, we've imported some of the variables you created last time. Specifically, we've imported the counter object, training counts, and the make review counts. This means the program won't have to recreate those variables and should help the runtime of your program. Begin by making a multinomial NB object called classifier. We now want to fit the classifier. We have the transform points found in training counts, but we don't have the labels associated with those points. We made the training points by combining neglist and pause list. So the first half of the labels should be 0 for negative, and the second half should be 1 for positive. Create a list named training labels. that has 1,000 zeros followed by 1,000 ones. Note that there are 1,000 negative, 1,000 positive reviews. Normally you could find this out by asking for the length of the data set. This example, we haven't included the data set because it takes so long to load. So how do I do that? Training labels, you can use the asterisk operator to quickly make so 0 times 1,000 plus 1 times 1,000. Call the classifiers .fit function. Fit takes two parameters, the training set and the training labels. So so we haven't loaded the data set, right? Your training set is found in the variable training counts. Okay. And the training labels are on training labels. Call the classifiers .predict method and print the results. So when we pass it our view counts, we got a 1, so it's positive. After printing predict, print a call to the predict problem method. Parameter to predict problem should be the same. So relatively strong prediction. I mean, not great. I mean, 77. First number printed is probably the root was bad. Second is good. Change the text review to see the probabilities change. So crib was bad. Interesting. Can you create a review that the algorithm is really confident about being positive? The review, this crib was great, amazing, and wonderful. Had the following probabilities. Can you create a review that is even more positive? There we go. Review. In this lesson, you've learned how to leverage Bayes' theorem to create a supervised machine learning algorithm. Here are some of the major takeaways from the lesson. A tagged dataset is necessary to calculate the probabilities used in Bayes' theorem. In this example, the features of our dataset are the words used in a product review. In order to apply Bayes' theorem, we assume that these features are independent. Using Bayes' theorem, we can find probability of class given a data point for every possible class. In this example, there were two classes, positive and negative. The class with the highest probability will be the algorithm's prediction. Even though our algorithm is running smoothly, there's always more that we can add to try to improve performance. The following techniques are focused on ways in which we process data before feeding it into the naive Bayes classifier. Remove punctuation from the training set. Right now in our data set, there are 702 instances of great exclamation mark and 2,322 instances of great period. We should probably combine those into 3,024 instances of great. Lowercase every word in the training set. We do this for the same reason why we remove punctuation. We want capital G great and lower G great to be the same. Use a bigram or trigram model. Right now the features of a review are individual words. For example, the features of the point this crib is great are this crib is and great. If we use a bigram model, the features would be this crib is, and is great. Using a bigram model makes the assumption of independence more reasonable. These three improvements would all be considered part of the field of natural language processing. You can find the baby product review dataset there. In the code editor, we've included naive Bayes classifiers that have been trained on different datasets. The training sets used are the baby product reviews, reviews for Amazon Instant Videos, and reviews about video games. Try changing review again, see how the different classifiers react. This game was violent. So, Amazon video training set says it's negative. Video games training set says it's positive. It's funny. What is the purpose of smoothing in a naive Bayes classifier? To prevent a feature with a probability of 0 from rooting the total probability. That's correct. If any feature has a probability of 0, the multiplication will result in the total probability being 0. Given the following word counts for positive and negative reviews, what is the probability of great? Probability of great. So 2 out of 3, 6, 8. So 2 out of 8. And so that's 1 in 4. And 1 in 8, 10, 12. So 1 in 4 plus 1 in 12. 1 in 4 is really 3 in 12. So 4 in 12 is 1 in 4. I clearly got that wrong, huh? The total probability of great in general, right? So it's 3 in 12 plus 8 is 20. So 3 in 20 is about 150. Yeah. Given the following word counts for positive and negative reviews, what is probability of great given positive? So if it's assuming that it is positive, the probability of great is 1 in 4. The predict method in the multinomial naive Bayes class takes something as a parameter and returns something. Takes a list of data points as a parameter and returns a list of classifications. Takes a list of data points and returns a single classification. Damn it, I should have known that. I knew that. Whatever, doesn't matter. We can ignore the denominator of Bayes' theorem when calculating the probabilities of each class. Why can we ignore the denominator of Bayes' theorem when calculating the probabilities of each class? The denominator is the same for every class. The denominator will add to the error. Bayes' theorem doesn't have a denominator. Correct. P data isn't dependent on the class, so it is the same for every calculation. Why is a naive Bayes classifier a supervised machine learning algorithm? The algorithm learns from a reward function. You need label data in order to calculate the probabilities using Bayes' theorem. Algorithm unlabeled data in order to make classifications. We're going to use smoothing, so it's this. Which of the following is not a natural language processing technique that can improve performance of a naive Bayes classifier? Punctuation, so smoothing. While smoothing is an important part of a naive Bayes classifier, it has nothing to do with natural language processing. If the target names of a naive Bayes classifier are BADC and the predict proba function returns the list 0.3, 0.1, 0.5, 0.1 for a given data point, what is the predicted class for the data point? So again, the target names of the naive Bayes classifier are BADC, and the predict proba function returns the list 0.3, 0.1, 0.5, 0.1 for a given data point. What is the predicted class for that data point? So it's predicting that it's class D. No, it's terrible. All right, so email similarity, which I'm not going to do. So when I get back to this, I'm going to be doing unsupervised learning with clustering, doing k-means clustering. Excited for it, but that's not for now.